Check, check. They should have been able to hear me. I don't know what's going on. Oh, and thank you, Josh, for helping me run that stream earlier. That was helpful.
Yeah, StreamYard can be a little bit buggy. It's kind of finicky sometimes.
Yeah.
So like I couldn't talk to anybody while I was doing that, but that was okay. I didn't really have any questions.
Right.
I mean, I'm not a physicist. I'm here. I'm along for the ride. I think this stuff is super interesting, and I end up learning more than I going to stuff like this than I would just by, looking up random YouTube videos. So I end up sitting here and Googling things constantly while you guys are talking.
Yeah, I realized earlier they couldn't hear my audio, and I unmuted myself, but I have to add myself to the StreamYard thing, and that's why I wasn't like coming through on the audio. So it's just like if you don't do all these things, it's like there's all these little bugs and stuff. And then trying to get Zoom to work in conjunction with StreamYard just always causes me issues. But I figured it out. I got home.
So I have an open question that I'll just ask all of you. It's kind of about what Bob Greenyer was presenting. We were talking about how he talked about like teleportation and wormholes and creating energy and destroying energy and creating matter, and how it defies some of the existing laws of physics. Do you think that it could be related to like the idea that there's hidden terms in some of the equations that are currently set to zero? Maybe when you put something behind, what was it? So some of the particles that he was presenting, that maybe they're changing the local laws of physics, like inside the ball lightning, for example.
I wasn't going to chime in, but you nailed it. You nailed it.
Okay.
That's exactly right. The stress energy tensor of the local space-time is being modified in a specific way. And the nature of energy distribution results in a localized, I guess you would call it localized space-time, or a reference frame that is separate from the external reference frame of the observer and all the surrounding matter.
Right, kind of like in a bubble. So it's kind of fits in with the warp field theory, where if you can create the bubble where you can change the laws of physics, you can move faster than the speed of light.
Exactly. That's what we're attempting to verify with our antenna structures, is that we are in fact affecting and storing up an amount of real physical energy as an electromagnetic waveform in a canceled momentum vector in the local stress energy tensor of space-time. And the way we intend to indicate that is using laser interferometers to demonstrate a delay in the path length of the photon, or what I guess you would consider to be an increase in the path length in the photon.
This guy, I'm just reading some of the comments here on YouTube. This one guy said he's like, every APEC conference, at the end, I end up with 47,000, like 50 browser tabs open with all the stuff that I have to research in Google, and I can't read a single one of them.
I'll actually have to go back to the beginning of this thing. I had missed the first 6 hours of it.
Yeah.
Definitely definitely watch Bob Greenyer's presentation. He did a full 2 hours.
I caught the last bit of that. It was amazing.
Guys, it took so much effort to try to get Bob. And I remember trying to plug him with APEC the first time on his channel during a live stream. than the email stuff. So it's like, we've been trying to get Bob on forever. And I knew when he came on, he's going to be a beast. And, the sad thing is I only seen like 20 minutes of the beastly presentation, right? So it sucks, but I'm going to go back and watch the whole thing. Either way, it sounds like he really did tie it all into what we're working on as well. I knew there was a lot of potential in Ken Schulder's research with EVOs regarding propulsion and energy, and he had really covered a lot on his channel, and obviously now he's revealed the reason for why he was told not to talk about it. I think that's pretty freaking great, and I'm super glad to hear that he's on board, and I know that he knows. I knew that he knew. It was just a matter of getting him to get involved with this community and realize that, we're really all on the same page here. Even the stuff that he's doing, which he's kind of isolated and fringe in his own, academic community, but amongst us, he's quite welcome. So I think it's great.
Yeah, it was an incredible presentation. I mean, I've watched hours and hours of videos just on the Martin Fleischmann Memorial Project's YouTube channel. And he tied so many videos together. And like, I saw video clips and images that I've seen before in the videos, but I've never seen him put them in that order before or explain it that way. It was really interesting.
I've had people actually track me down and email me specifically to ask me if Bob Greenyer is genuine and if he's actually talking real stuff or if he's actually making it up, because it sounds so fantastic about transmutation of metals using exotic vacuum objects or electron clusters. And I'm like, believe it or not, folks, this is the real deal. It's been done for a super long time and all the evidence is there. So
I've been following him around the internet for several years, and like, I've heard him talk about a lot of that stuff before, even some of it extending back to like Tesla and even before Tesla. Like in the 1880s, there was a chemist that was doing experiments with chemical reactions and exposing them to electromagnetic fields that were tuned to specific frequencies. And he used a completely different language to describe it, but it sounds like he was achieving transmutations like LENR.
Do you guys remember the Odic ray? The Odic ray is, you can find it on Rex Research, ODIC. Anyways, it was yet another electron acceleration type device, much like an X-ray tube. And it was designed to produce fast acceleration pulses where the momentum was neutralized at the end of the electrode and the rest of the momentum wave was carried out as a matter wave that would shoot out the end of the ray. And he could apparently disintegrate matter. And what my guess would be is that if you accelerated electrons towards an anode and they turned 90 degrees before they struck that anode, then basically the entire acceleration path along which they were traveling through the vacuum tube would have, because they're not actually losing their momentum or stopping in the same directional axes as they accelerated, the extra momentum or acceleration of the relativistic electric wave, just like a synchrotron laser, would end up traveling outwards past the output window. And any matter that was in the way, should it have to have the correct spacing of the wavelength for that transmission and the distance between the individual atoms, you can rip electrons out of that structure. And it turns out that any matter, no matter what it is made of, if you rip the electrons out of the valence bands to the point where all the atoms are stable on their own without covalent bonds, they simply gellify and fall apart. But the Odic ray is just one of many devices that uses the same type of model with an unbalanced acceleration where you neutralize out the momentum wave in a directional axis that does not cancel out Newtonian wise with the momentum wave that's produced. Boeing has a patent for a momentum wave generator. And then there's also the Morton effect. I don't know if anybody's ever heard of that, but our research team is working on the Morton effect. One of our researchers from Vietnam has already successfully produced it. It is a pulse beam or a force beam that can move a piece of paper or something hanging inside of an enclosed cage. And I've also replicated several versions of it. I'm working on actually replicating a Vietnam version right now, just so I can verify that everything he did is in fact valid. And then we have 2 verifications of the Morton effect, and it does the same thing. It's another electron acceleration device. So there's a lot to electron clusters and the differential energy that they carry. And when you distribute the energy and the clusters break down, all that momentum has to be returned. So it is, and it equals a force that is akin to gravity. I can't say it is gravity, but I can say it's quite akin to gravity, as in it attracts or repels all matter universally. It doesn't matter what the hell it's made of. But I will say that what the matter is made of does attenuate the velocity of the wave through it. Hope I didn't lose everybody on that. Jeez.
All right, I'll ask a question. Maybe this has already been answered, but how do you make an EVO?
One of the ways that it's
Anybody
been,
catch that?
what's that?
Did anybody catch that? How to make an EVO?
Yeah, can you guys hear me or no?
I think it's nonlinear optics. It's anything that breaks the Schwinger limit. So it will create an exotic vacuum object or a nonlinearity in the vacuum structure. But maybe I'm wrong.
Specifically, what we've researched, and it's not been answered even quite exactly by Bob in the engineering sense of what you want the magnetic structures to do. But just imagine this. Okay, so imagine that you have a momentum wave of electrons that are accelerated and they strike a target at 90 degrees. So the momentum travels outwards. They can squeeze the electrons out of something. When a bunch of electrons exit an object all at once, they would generally just repel away from each other and try to find out some other point where they'd try to swing around the other side and create an electric field and neutralize around to the electron depleted region of the material. But in this particular case, the material is experiencing a magnetic field because of the flowing currents in the plasma surrounding the object. So it's generally done in vacuum for the most part, and a plasma is used in order to create a surrounding magnetic field. So instead of the electrons just simply being able to exit straight lines and neutralize out on the positively charged side of the material, what they do is they create circles. And when they circulate, they reinforce the B flux. And so what will tend to happen is that an electron that moves in a straight line, if there's an electron directly behind it or almost along its path, the electron will try to move directly into the line path of where the first electron had moved already. This is the same thing that happens in lightning bolts, where the leader electron creates an electrically polarized region of space where other electrons can more easily move into the path. So electrons in a beam will tend to narrow out the beam, even though normally if they were stationary, they repel each other. If you get them all moving in the same direction, they'll actually try to focus in towards a tighter beam path where they take up less area. It's one of those strange phenomena that charged particles do too. It's the same thing with matter waves. So to create EVOs, all you need to do is pass a large quantity of electrons, leaving an object through an intense magnetic field so that they circulate, and they'll tend to follow each other into a circular path where they're now spinning and they reinforce their own spin. And they have angular momentum because they're traveling very fast, but they're not technically moving through space relative to other objects in any kind of particular direction except for their angular momentum. So they're like little gyroscopes made of pure electrons traveling at near relativistic speeds. Just imagine the angular momentum of a cluster of 12 or 8 or 14 or 100 electrons traveling in a big ring at near relativistic speeds. You can imagine just what kind of magnetic fluxes these devices can have, or these electron clusters can have. So yeah, all you do to create it is you have an electron emission source, could be a cathode, could be some kind of material that has high temperature like a tungsten emitter, and then you have a vacuum environment and a high voltage pass between your cathode and your anode. And you'll actually see these objects, these bright spots appear on the electrode, and those are EVOs. And they'll do interesting things like transmute the metal of the surface of the electrode that they're on. And if they happen to fly off and hit something, they'll transmute whatever they hit.
Hey, look at that. The amp is working. I mean, the dial at least is working. I'm not going to power it up fully until I put the cover back on.
Way to go, Mark.
Yeah.
What a beautiful amp.
The only place that had the spare part was the guy who sold it to me. And he just sent me a spare. I sent him a text message. And he sent me a spare, and now it's working. At least that part of it is working. So if this ends up working, I'll be able to power up that warp contraption over there. But I'm waiting for some circulators to arrive to protect the circuit. They should be here later this week. then I could do it safely without damaging anything.
Oh yeah. I hear that. Don't forget about the attenuation losses of the circulators too. Some of that stuff can actually cause problems in the harmonics phase delay, but I'm sure we can figure that out. I've been learning so much about RF, dude. To be honest, I've just been on a total kick, educational course about learning RF equipment on the hardware side because I know RF from Tesla Tech. Not Tesla Tech the conference, but Tesla technology in general, just from studying it. And I can tell you that in the megahertz regime, in the lower frequency range, it's not at all the same when you start to get in the super high frequency range. So just learning the hardware and making it all work and realizing what equipment I need. It's like, I see why you spent probably, over 300, 400 hours on Amazon just trying to find these freaking parts and searching eBay and going to these freaking labs because, geez, trying to find the stuff that you need for a specific experiment, especially alpha being extremely specific, it's not easy.
Yeah,
So,
that guy, Bob Greenyer, he's very interesting. He's the first one I've ever heard to use the term coherent matter, and he's used it over and over and over again.
absolutely. Bob is a genius guy. He spent a tremendous amount of time doing his research on this and doing experiments and collaborating with other experimenters around the world. So, like, this guy is into it. He knows his shit. He knows what he's talking about.
Yeah, he definitely knew what he was talking about, and he had a lot to talk about too.
He could go on for hours and hours and hours, man. It's almost an endless pool of knowledge. But he definitely is specialized in specifically the research of Ken Shoulder's work and the variety of applications that have stemmed from it.
That bit does not sound very healthy. I'm gonna let it finish though. I think I chipped it. That face mill. Oh, okay. What's going on at the Milwaukee lab?
Oh, quite a few things are going on at the Milwaukee lab, but I did just want to comment on how good the Falcon Space Lab is looking there. Right? I really like the white shelves. It looks decent. Like, as you were panning by with the camera, I couldn't help but notice how good it looks. So,
Yeah, it's like every table over here is now a workspace where you can work.
and I really like the white.
Why are you coming down?
Well, apparently I'm delayed because I needed more than I thought I needed. And as I learn more about RF, I'm realizing I really need to understand what's going on with this stuff. Even the effects I'm seeing, I can't quite quantify. And you don't have any more equipment than what I have right now. So what I need is specialized stuff that I didn't know I needed. And I'm now trying to allocate.
What do you need?
I need a very wide sweep range signal source that can run off battery power and does not generate shit
I
waves.
have two of them. I think it goes from 20 megahertz to 18 gigahertz, just a noise generator.
Yeah, that's not what I need, dude. I've got a bunch of stuff on order. I've got some other stuff on order as well to do various other experiments. So right now I'm replicating I don't know if you've ever heard of the T.T. Brown research with photo gravitic effects.
Wait. So what is this noisemaker that you need exactly?
Hey guys,
I don't need a noisemaker, right?
Can I make one of you gentlemen the host for the remainder?
You can, but give me a minute because I have to log on to my computer account.
Okay, or I can do
Oh,
Mark.
you can do that for me.
Mark? Okay, I'll do Mark. I'll do Mark. Thanks. I should apologize for being, as you guys know, I'm a little distracted this week, but hopefully I held things together. Okay.
You did. You did a great job.
Oh, thank you, sir.
Round of applause for Tim.
Always, always.
Now I can go fall apart at the seams in private.
Oh, look, there's Lulu.
Okay. Thanks again, guys.
Give me a second, Tim. I'll just hold on for a second. And just let me in real quick. Let's see. I'm connected to audio. Great.
Do you need a wideband something?
Oops, you know what? That was not the right link. And meeting for all. Yeah, never mind. No, I just need to open this up real quick.
You needed a wideband something?
Give Give me a second, Mark. I'm just trying to get into the Zoom from my computer so I can have my full Zoom privileges, my admin stuff on there, because the account I'm on my cell phone. Right?
He's already given it to you though, Mark, right? You don't need to,
Yeah, I'm the host now. I can
Are you
figure it
okay?
out.
Transferred.
Yeah.
Yeah, there you go.
Okay. Is Martin Gardner David Fisher?
Good question. I genuinely don't know.
That's what somebody wrote in the chat. Can you guys hear me?
I can hear you.
Okay, good. Yeah, Martin Fisher is David Fisher is actually one of my father's friends. He lives down in Lakewood, and he worked at Bell Labs, and he knows a lot about RF. He was the guy who invented the amplifiers for fiber optics that were passive fiber optic amplifiers. You just stick it around the cable and it can amplify the signal. Really cool stuff.
That work.
I mean, that's probably how we're communicating right now, was through something that David Fisher invented.
I'd like to know how a passive fiber optic amplifier works. I've never heard of that device. Sounds like something I need to look up and research. So I have exciting news.
I like exciting news.
Do you remember the asymmetric, or what was it? It was the paper was called Bidirectional Forces from Accelerated Electrons through a Dielectric Barrier, or something on those lines. It was very close to that. Anyway, so what it talks about is that same electron acceleration model that it was just talking about, the force beams of the Morton effect, and it technically applies to Pockenoff too. So that effect, one of those papers, including the Horizon drive with Michael Kalish, was similar because they both use electrodes juxtaposed to each other through a very, very thin film dielectric. And there's an information horizon regarding the space behind the cathode that can affect matter behind it. So if there's a significant amount of mass behind the cathode, the entire device ends up creating a force towards the cathode. But if there's nothing behind the cathode, it's just the cathode electrode, then it ends up generating a force towards the anode. So it was kind of interesting because there seemed to be this spatial information horizon that died off with something that was slightly different than the inverse square. And so I got one of those materials, and it was recommended. I don't want to say what that material is specifically yet, but that I tested it earlier on the Megger, and it was demonstrating the leakage properties that were called for specifically. And I've checked 12 different materials now, and none of them have this exact property like the particular material that I've just got in. So I'm quite excited now. And this is just the first of two materials. This particular one is twice as thick as the second one I'm getting in that I had to order for from overseas. So that should generate about 4 or 5 times the force of the thicker one. So I'm pretty excited about being able to generate basically a reactionless force thruster with this material, since it's such a simple design. It's just DC power and a couple of plates and this special material.
What is it, like a really high resistance glass or something? Or
It's actually it's a polymer. It's a polymer that has a particular thermal property and I'm theorizing here, but I took a kind of mental speculation and mapped out all the possibilities that I could think of. And the one that came to mind was electron tunneling makes sense based on the work of Richard Van Derek. And if you take a look at the model of how those charged particles are actually getting their charges, they're suspended in the matrix of epoxy, where technically the epoxy barriers between the metallic conductors are too large for charges to directly jump across. So how do they actually tunnel through and end up charging these elements? Well, the only explanation is that through Brownian motion, thermally, at some point, all the individual motion of the atoms around will open up in such a way that a charged particle, an electron, for example, can tunnel through and get locked into the matrix of the dielectric tunneling into it. And if the thermal motion opens up in such a way that it can continue to move towards a lower state of charge where there's less electrons, so especially with the metallic electrode where the electric fields are concentrated around it, then it will manage to make its way through slowly, and that depends on the temperature. So heating the material increases the leakage flow without actually destructively working with the material. So the dielectric leaks, but it doesn't get damaged. And a force that's experienced in the information horizon of the drive resolves.
okay, very cool. So you got some of this material in.
Yep, I've got the first of two different materials. I've got the thicker stuff, which is supposed to be not quite as good, but easier to work with.
Very, very cool. I need to figure out how to put together this laser interferometer. I'm still waiting for one more part, which is the expansion beam holder. And when that arrives, I can put it all together.
Yeah, we'll get on a Zoom, talk about the stuff that you need to CNC, and then once it's all CNC'd and made, then we'll get on another Zoom and we'll talk about how to put it together.
It's all CNC'd already. I already got a diffraction pattern and all that. It's just that I have to hold that last mirror needs to be held by hand because I didn't get the holder for it yet.
Oh, that's fantastic. Very good, man. It looks like it's coming
I
right.
also have extra mirrors too.
Yeah, it's useful to have extra per surface mirrors, especially if they get scratched at some point. You can just replace them.
We're almost finished over here. This second pair of holding arms for the gyro system. That'll be pretty cool. Aiden's going to be here pretty much the entire month, December 13th through January 6th.
Well, I guess there's just pretty much no way in that his Benellis device isn't going to get finished then. And it sounds like I did not expect this, but apparently Bob Greenyer is familiar with the Benellis device. And when Aiden and Bob get to working on that together, I can almost guarantee you it's going to get solved.
Right. Yeah. So if we can get Bob down here too, that'll be pretty cool. Any chance you can make it down in the month of December?
Bob's not even in the United States, so I wouldn't worry about trying to get Bob down to the lab. It's not really important that he goes down there. Just rely on Bob's decades of experience. He's glad to help. He loves this stuff. He's passionate about it. Work with him. Don't try to get him to come down. He's got way too much going on at home, but do acquire the knowledge, and we'll make sure that Aiden and Bob get connected in a way that works for both of them.
I also have this other guy, what's his name? Paul Johnson, who's like super passionate about working here. He came down for a week. He was here with Aiden. He introduced himself as a welder, but it turns out he's much better at math and taking notes, really. He wants to put a curriculum together based off of this technology for college.
Oh, and I think that's a fantastic idea. I think everybody from Todd to myself to, Valone have all had that kind of idea that we'd all want a curriculum put together if we actually had something that was so tangibly provable and repeatable that it could become common science. But honestly, we're a far ways away from that. And I can assure you that once it becomes common industry knowledge, colleges will inevitably adopt it so that they can still be relevant to teach kids things that are industrially applicable and increase their profitability according to
no doubt about that. But if you already have a book available at that time,
it's a good place to start. It's a good place to start.
Yeah, it's a great place to start.
Honestly, nothing is going to speak to the world like an actual industrial product that can get out there and be used now. All that theory is very nice, but you're not finding CERN in textbooks except for by passive reference. And it's not going into great detail unless you're specializing in a course that teaches you about, particle physics models and theoretical sciences. So if your specialty is in astrophysics, you're probably not reading about that stuff anyways. And yeah, so the thing is, we need practical models. And right now, I think the greatest schools in the world are trade schools because they teach you things that are actually utilizable. And I know MIT has a reputation for being, a highbrow academic place, but honestly, MIT is as much a trade school as it is anything else. They do generate real technologies. And although they might not teach you about current trades as much as they teach you about how things work, they actually generate industries from nothing. MIT has generated huge changes into the LED industries, for example. So not all of academia is corrupt.
No, of course not.
A lot of it.
I was thinking of heading to NJIT and putting up a flyer there offering, to come work in an anti-gravity lab. Warp drive technician. That's how Paul Johnson actually found out about this industry. He saw that that job opening that I put for a warp drive technician. He thought it was SpaceX at first. He didn't realize it was, Falcon Space because the names are similar. And he quit his job at Caterpillar and started going to college thinking that he'll work for SpaceX as a warp drive technician.
Oh, boy.
And then he realized that college was just taking his money and he was learning from a book. So he quit college and continued learning from the book.
Yeah.
And he also found he could get the books for a lot cheaper too.
Hell yeah, absolutely.
I tried running an ad like that in my area for just volunteer engineers and stuff like that. I think I got one response.
Really?
Yeah, I just ran it in like some local classifieds. So I guess we're not quite there yet. Yeah. But the guy that responded, he was a doctorate in mechanical engineering, so it was kind of, but he didn't seem to understand like what. It's kind of weird. Didn't really understand, like he wanted to help out with APEC, but he had no background in experimentation with, propulsion, electromagnetic propulsion, or anti-gravity, or.
I mean, you don't really need a background in that. From my viewpoint, most of the stuff that happens here at Falcon Space is arts and crafts.
Well, it's high risk. It's it's highly speculative, and it's like just trying a bunch of stuff, seeing if it works.
But most of the work, at the end of the day, most of the work is arts and crafts.
It's probably alchemy is the best word for it. Like we're just, I don't know. For me, anyways, there's still a lot, even with Alzafon's theory. I mean, there's still like a huge amount of tinkering to do. Like it's after 40 years since that was published, still so many variables, so many unknowns.
Number
I
one,
agree.
I'm up
Same thing,
against.
the T.T. Brown stuff, you know, that's like going on 100 years old since he discovered it. We still have all these questions. So
At least we understand what's going on with T. Brown now. We now understand what all that rigmarole was about, the strange things in his papers and his patents and in his notebooks. So one of those things that I swear, man, everybody overlooks this except for Van Dyck. And they overlook the injection of metallic particles into the dielectric as some ancillary thing. Oh, he did that to make it heavier. Oh, he did that for this reason, that reason. No, it has nothing to do with any of that. It has to do with getting a particle density strong enough to allow charge tunneling. And people just understood.
He might not have even known that.
Oh, he knew.
Well, he
He knew.
didn't let on in his papers. He made it sound like that was for weight.
No,
You know,
that's not what he talked about.
initially-
Concentrating it on one side of on one just electrode compared to the other. Like he made quite specific points about concentrating the particles being a lot closer to the small electrode. They're closer.
You're talking about T.T. Brown, right?
Yeah.
Right.
Yeah,
You
the
have to
tape.
read his yes,
paper
four note-
structures.
What do you think of Podklanov and his response to Charlie? He wants $200 million in 6 or 7 years.
Pakhanov sounds like he's gotten very, very soured by constant rejection from what should have been a professional community. Probably acting awfully childish and being disregarding towards what's very high potential in serious science. But I think at this point he's almost gotten sarcastic with what he's asking for, just because he's so angry at how much he's been ignored and laughed at in the community. I also think he's gotten threatened enough times to probably have a thoroughly justifiable concern about the safety of himself and his family.
Mm-hmm.
Sounded to me like
Maybe we could start by like offering him a ticket, you know, all expenses paid trip to the US and come work on the whatever experiment you want to work on.
Yeah, you should talk to Frolov about that, and talk to, again, George Hathaway about that, who had Podklanov down at the Hathaway Labs to help with their replication of the Podklanov experiment, which, as Hathaway told us, was a tremendous disaster. Podklanov was angry because the experiment wasn't working, and Hathaway was upset with Podklanov because he was not able to figure out why it wasn't working. But according to Hathaway, they used a single layer superconductor, and Podklanov apparently never made a point of noting that it wasn't going to work, which then goes back to what we heard from what's his name now? The guy with the garage lab in the background setting, Glenn. Yeah, so
Tony Robertson.
Yeah, Tony. Yeah. I always get them mixed up because he's got this, you know, he's got the whatever shorthand name, which is the same number of letters as his regular name. So anyways, yeah. Glenn, Tony, talk to us about.
His name is Glenn Anthony, actually.
Glenn Anthony, yeah, okay. So I'll never remember exactly what the heck his full name is, but either way, the point is the guy knows, and he's done enough research on Ning Li to say that basically Podklanov was only copying Ning Li's work, and she was the one that really had figured out exactly what the correct mixture of superconductors and junction materials were. And who else figured that out? We know that Bohr did, because Bohr talks about the multitude mixture of materials, but is quite specific or is quite secretive about that mixture. And then we have Black Brains project, and I want to point those guys out because this is important to note. Black Brains was posting about their drive. They had replicated Bohr, and actually at the end of what they were doing, publicly posting, just like Bohr had last publicly posted before they went silent, they said they found a room temperature version of the device that did the same thing. And Black Brains said that they had found a room temperature version of their system that operated as well as the supercooled superconducting version. And that's exactly when their WordPress site went down, when all of their social media went down, when they took their YouTube videos down. That's when everything went dark. So the second that both of these places found a room temperature version, They all went dark. And what does that tell us about whether or not we should be looking at what they had done prior to that? Pretty significant stuff. Somebody doesn't just disappear after a tremendous series, a string of successes for no reason. You know who else is going dark? Richard Van Durick. He's not even working on all that mechanical stuff anymore. What they have now is literally solid state and can, I'm sure, lift its own weight by this point. Look at these people who have posted stuff that works and have a series of successes, and then see when they disappear to know that you are looking at something genuine.
Maybe we should start disappearing.
I've done plenty of that myself for the things that needed to be quiet, but there are things that I need to bring out there too, and I'm just trying to figure out the best way to do it.
Please leave your message after the call. After leaving a message, you
Oh, there we go. Yeah, you've disappeared quite a few times. Various reasons.
And data security, man. I've been compromised quite a few times.
Now I'm getting ready to move on to the next step. Okay, this is not going to work.
We've also got that molybdenite sampling for testing low frequency potential DNO. According to the strange and having now disappeared AAG post about it, molybdenite, the naturally occurring mineral containing a high content of molybdenum and sulfur, apparently can generate an emission of electrons traveling at near relativistic speeds, which generate what they call electron photons, which is just basically a scalar compression of the field in front of the direction of the electron, just like a synchrotron laser, which is an electron photon device. So anyways, this device apparently would lose momentum along the axes of the grains, and that's towards the edges, and it would gain momentum along the bottom and top of the grains for perturbation of a low frequency AC magnetic field to push charges out of it. So just like Ron Kita's patent, it's supposed to be a gravitational attenuator. Something heavy placed above it should get lighter.
1 second. So molybdenite, what do you do to the molybdenite?
You pass the coil around it. I'm going to use a Helmholtz coil just so that we can remove from question whether or not we're generating some kind of strange directional forces. And it's possible to generate a gradient magnetic field by varying the current going to either of the 2 coils for the Helmholtz coil, although you could also generate a gradient with physically different geometrically sized coils, but I'm not too worried about the gradient. What I want to really see is that it can polarize momentum along an axis, take it from one and put it along the other through precessional reorientation. Bismuth thin films also exhibit the same property, and we also are quite aware that graphene nanotubes can do this too. But it is interesting as a concept to think that maybe molybdenum or molybdenite with its particular structure could be capable of doing this.
Tom Schoenborn is going to be working with us on a vapor deposition system.
Indeed, I'm quite excited about what Tom can pull off there with you guys. I think that's going to be a really great thing to have. I mean, I tried to get Wayne, to work with that system that he's got, and Wayne's system, I guess, has a few problems. He got it for a good price, and it's almost there, but I think he has an issue with one of his pumps. So I don't know. It probably shouldn't cost too much to get it working.
And also
Wayne, you break.
hear me?
Hear this? Hello?
Hello?
Okay,
Yeah, we can hear you.
Okay, I wasn't sure if you could hear me or not. Yeah, I just
Not
heard
a-
you
Yeah, you're
talking. Yeah, the melter, or whatever you call it, the part where you put the metal and it melts it, the heater, whatever, I don't know what it's called. Anyway, that thing broke first time I used it. So I don't know. I just and the diffusion pump. I don't know how to test it. See if it gets hot. So I know it's supposed to warm up, but I don't know if it's doing what it's supposed to be doing. Kind of.
Is it an oil diffusion pump?
Yeah.
Okay, so it has hot oil on the inside. The outside needs to be cooled down with water circulation. There should be a tube that surrounds it. You got to pump water through it.
Yeah, there's a water pump and tubes and stuff around it.
Does it have liquid in it, and is water circulating, or is there air in the line?
I don't think the water circulates. I didn't recall seeing it circulate. No.
Okay, well, get that working, because the diffusion pump actually relies on the cold outside in order to condense out the contaminants.
Yeah, I don't know. I'm kind of overcrowded right now, so I don't have much room to do stuff anymore.
Yeah, room is an issue.
I'm gonna need to rent a hangar or something.
Oh, I know some guy who has a hangar.
Oh,
I need a 10,000 square foot hangar. Yeah, and I could do something serious.
I really need about 6,000 square feet. I think that's going to be what the lab space requires to set up the kinds of things I want to do. And the other important is fairly tall ceilings.
I don't think 6,000 square
What?
feet's going to cut it. No. Stage 2 needs more like 15.
Consider it stage 1.5.
Why even bother? Do you know how hard it is to move a lab?
It doesn't need to be a moved lab. Nothing needs to move out of that location. That location is R&D. I can build a craft in a location of that size that I can personally sit inside and do what I've always wanted to do, which is build that personal flying platform.
I don't think 6,000 is going to be enough. I think that's
25,000.
25,000 is nice if you get something that large. Jeremiah, 6,000 square feet is 2 times the size of the Hawthorne lab.
Yeah, that's exactly what I need.
Nah, I think you need more than that.
I don't know. That's a good 12-person operation there.
Hey, can I want to back up and just share a bit. You're talking about the superconductors there. I overheard a little bit there. I made a little video and stuff a little while ago, a few days back. I suspended a brass. It'd be easier just to explain it on video, but anyways, I suspended a brass weight above the superconductor, cooled it down, and then I was recording the weight continuously, or at least every minute. And then around some time afterwards, I guess as the liquid nitrogen vaporized and the puck started to warm up, it looks like there was quite a jump in the weight of the sample. So it went lighter after this sharp cliff on the graph. And I suspect that that's the point where it went from superconducting to, non-conducting. So
Interesting. Do you have a video of that? Did you take a video of it?
yeah, I did a little video and I got the data. I haven't shared it yet. And oh yeah, I was gonna say, a second. You weren't there today, but Frolov was talking about the superconductors and how they make forces when they cross the critical temperature. And I saw this in Martin Tamar's paper as well in 2005. So yeah, it's interesting. I think it's worth playing around with some more.
I would have to agree. And
Yeah.
we're looking at bismuth thin films as well, because they exhibit those same kinds of properties. It's one of those things that has yet to be thoroughly explored, in my opinion. And so for the preliminary papers that work with very small scale structures are showing incredible properties. One of the things I noticed and that I wanted to point out, bismuth, my girlfriend found this out after doing quite a bit of research, because she's now getting into the metallurgy stuff. Actually, I think she doesn't know where she wants to go with it specifically yet, but I have a feeling that we're going to end up going with the metamaterial science, just because what she wants to do, what these materials do, is going to require her to study metamaterials. She wants to tie the metaphysics and the metamaterials into each other, I think. But what she had discovered is that bismuth has a property under Hall effect conditions where a very thin film configured like a conventional silicon Hall effect sensor will demonstrate incredibly strong sensitivity to an externally induced magnetic field. So I'm sure everybody here is probably familiar with how the Hall effect works. Basically, just imagine you have a square of metal and you have four corners of this conductive plate. And from the middle of the square on the bottom, you pass a negative, current. And from the top of the square on the other side, you have your other wire. So your current kind of passes in a straight line through the square. And then on the corners of the square, you have pickup electrodes. And so normally the pickup electrode should measure that you have about the same differential voltage between the top side of the square where the positive electrode is and the bottom side of the square where the negative electrode is in the center. But if you pass a magnetic field through that thing, the bottom, so the north is facing the face of the plate, what will happen is the electrons, as they're passing through the metal, will be diverted to one side of the square, one of the corners of the square, and the other side will consequently develop a positive charge. So say on the top side, you'll get negative on the right and positive on the left, even though technically the electrons are still being pulled towards the positive electrode. And the reason for this is because the charged particles, the electrons inside the metal, curve just a little bit. Well, inside copper, they don't curve very much at all. It's hardly detectable. Inside silicon, they curve quite a bit more. And depending on the doping, they can curve more or less. But with bismuth, they curve to such an extreme extent that these sensors can be made retardedly sensitive. And the reason for why they curve has everything to do with general relativity and the electron velocity. So the fact is that bismuth works in this way and has these high Hall effect responses because the electron drift velocity of the charged particles flowing through it are so fast that Lorentzian forces tell us the velocity of the particle passing through a stationary B flux of the same intensity will cause a significant response in terms of the trajectory of the path for the already standing field. And this force is not necessarily reciprocal. So something
What kind of response time do they have? Does
What kind of-
bismuth has as a Hall effect sensor?
As a Hall effect sensor, the response time has to do with the physical geometry of the size. So if the path takes 1 nanosecond for the electron to traverse across the electron lattice, then your Hall effect sensor is going to respond with 1 nanosecond of time. It's how long does it take for an individual electron leaving the cathode to actually hit one of the corners of the cube, or one of the corners of the square, or whatever size pad you have.
The Hall effect sensors are notoriously very slow. Like,
no, that's because they have amplifiers inside of them. The reason why they have amplifiers inside of them is because they're notoriously weak in response. So they're slow because they use semiconductors to amplify the signal. But if you use bismuth, you don't need an amplifier because it's so fast that it actually generates the same kind of amplified differential voltage outputs at the corners that you would normally get from only a silicon amplified signal from a normal conductive Hall effect sensor. That was the point. Materials are directly useful in the analog sense. They do things that we normally require amplified electronics to do. And it's not like bismuth is even the best one. CVD graphene, for example, should be superior to that, but working with it is an incredible pain in the butt, and it's also very expensive.
And just something occurred to me about bismuth. So its conductivity is very poor, and yet it has a high drift velocity.
Its conductivity isn't poor, actually. That's a misnomer about bismuth. Its conductivity as a bulk multi-domain material is poor because the domains are extremely picky about the direction that the charges flow through them. And if they're all broken geometry in different axes, where if you break a piece of natural bismuth crystal that's cooled, you'll notice that if you crack it apart, you'll have all kinds of different lattices and directions, and you'll look at a structure that has all kinds of what do they call those things? Not echelons, things on the side of the Stargate. What do they call those? Anyways, whatever. So basically, you have all these lattice grains that form at pentagonal angles, and the thing is about thin film bismuth, it has the same crystalline lattice, so there are no broken domains, meaning that there's no restriction for electrons to flow completely across the lattice. That's the key. If you could grow a single large bismuth crystal that was a bulk material, and you could somehow control the electric or magnetic fields during its growth process and grow it slowly enough, you could have a bulk superconductor bismuth metal. But it does not naturally form like that, generally speaking, because it starts to cool at a point, and then diverting from that point, it has to cool outwardly, so you have a gradient cooling, and that gradient cooling naturally results in broken domains. If you don't have a gradient cooling, but if you have a what do they call that? If you have a laminar cooling.
What if you did vapor deposition?
Vapor deposition for bismuth is absolutely possible, but the problem that's been done in the 3 papers I've read about vapor deposition for bismuth is that if you use heat, like if you use a hot dish, like what Wayne's talking about, he has a tungsten hot dish that's burned out now, and he needs to pick up more of them. Luckily, they're cheap on eBay, but even that's not really ideal. The hot dish will develop bismuth vapors, and in an extremely high vacuum, where there's no other atoms in there, the bismuth vapors will hit the target electrode. But what they found out in the paper is that the bismuth, when it hits the target electrode, will tend to clump up and form crystals or balls on the surface of the, in their case, they use a sapphire substrate. So they formed like these little spheres of bismuth on the sapphire substrate that would not create a nice, thin, even single domain thin film. So their solution for it, rather simple. They took the window, or they made a window that would block most of the bismuth vapor, so it would hit the window, and then they would just pass the window across the surface of the substrate in, a back and forth direction at an even speed, so that none of these materials could build up these large crystals. And in that way, they were able to create a fairly decent thin film. I think you're trying to talk, Philip, but you're muted.
And did that thin film exhibit superconducting properties?
It did. Another patent that goes farther back talked about taking liquid bismuth in suspension of silicone oil, which is actually a type of oil, one of the only ones that can be liquid and non-evaporative at a temperature that bismuth is liquid within. So you have a liquid metal within a oil. And what they did was they took 2 electrodes, positive and negative electrode with fine points on them that were not reactive with the bismuth, brought them together in the bismuth pool, and then they stretched them out, and passing a current between the 2 electrodes, the bismuth had electrons traveling through it in one direction from the negative to the positive electrode, and that kept a nice thin line of bismuth connected between the electrodes, exactly like a water bridge between 2 flasks. If anybody's ever seen that with distilled water, you have a water bridge between 2 flasks as charges travel between those. And so that's what they did underneath the liquid heated silicone oil. And so then they just cooled the silicone oil with this thin wire bismuth stretched between the 2 electrodes, and ended up creating a monofilament crystalline bismuth wire that had superconducting properties at room temperature specifically.
Amazing.
I got an idea here. I was meaning to finish sharing. So with alternating current, you know the skin effect, right? So the current gets closer and closer to the outside surface. So in the case of bismuth, if you pass a high enough frequency of current, that current will become exist just increasingly on the surface, like on, a thin film, like a very superficial level of its surface. So I wonder if that would create an equivalent situation to a physical thin film. That's what I'm thinking. Like, you know what I'm saying?
No, I missed a little piece of that. I'm sorry. Give me just a second, Wayne. Give me like 30 seconds.
Okay. All right. So if you apply the concept of the AC skin effect to bismuth, so that the currents flow on a very superficial layer of its surface.
So how would you make? example, a physical example of this material that you're talking about?
Okay, so instead of going the road of trying to make thin film bismuth, which is probably a highly technical, tricky process to do.
We're working on it. We are working on it in the best way.
Forget the thin films, but I'm thinking you could get the equivalent effect by just running a high enough frequency current through the bismuth, because the current would exist on the superficially, on the outside surface.
Use scalar fields to do it, huh? Interesting.
Are you hearing that?
We talked a lot about how to do it when we were growing a bismuth crystal. So we got a whole setup to grow bismuth crystals in a very particular fashion. We've got the white sand, the high temperature, already kiln baked white sand that's not going to smoke and be nasty. I got a heating element, a stainless steel pan that I can place all this stuff in so I can maintain and control the temperature. Stainless steel melting flasks, and I've got plenty of bismuth now. I just got the order in for several more pounds of it. So we're going to start by just basically trying to control and create a very, very uniform and even bismuth crystal. So the first step is just being able to generate a natural crystal that is extremely uniform in its properties. Then the second pass is to generate that same exact crystal by passing current through it as it's growing to see the change in geometry. The third pass is to use an externally induced magnetic field to see if it changes the crystalline geometry. And then the fourth pass is to actually combine both the externally induced magnetic field, provided that there were results with one or the other, and at the same time, the electric field that's passing through as a flowing current, to see if we can then generate a significant change in the crystalline geometry. So what I'm looking for is actually a change in the bonding geometry. It normally forms, like I said, a pentagonal bond, which bismuth has a 3-5 ratio of outside valence electrons. So it has 5 valence electrons, but it can easily lose 2 of them and still be pretty happy and share them with the outside. And those actually become free electrons within the single lattice or within a single domain of bismuth. And so you end up getting triangular structures in bismuth instead of pentagonal structures when you get those kinds of bonds. But when you get superposition crystals, you end up getting pentagonal crystals instead of triangular crystals because of that same type of bonding geometry. And these materials also have different.
All right, so you're really doing a study of making bismuth.
Well, not just, but I mean, bismuth is the thing that we're using because bismuth has these properties that are controllable. So we're using bismuth as sort of a demonstrator, if you will.
Yeah.
Just to say, we can control the growth of types of crystal materials.
You remember that video? I think you shared that video where I don't know if it's true or not, but there's all stories about bismuth or wires coated with bismuth and how it would make these strong
Yeah, that was me that shared that video. I have it saved in my anti-gravity required knowledge playlist.
Yeah, and then so I was listening to Paul Bazar recently, and he was explaining his experience with this material and how it would, he tried to push his hand toward it, and then it would push away, push his hand back, and there was a repulsive field there. And so moscovium would have the same electronic structure as bismuth if it can be produced in a stable form.
Bismuth is actually right above it in the periodic
that's
table.
what I'm saying. Like on the periodic table, the columns represent atoms or elements that have the same electronic structure as you go from column to column. So all the elements in the vertical column have the same properties chemically because they have the same kind of valence structure right on their outermost shells. So
and the main thing again with a thin film bismuth, my goal wasn't really just with the thin films, it was being able to produce them, because the cool thing about vapor deposition, and not heated vapor deposition, but particularly laser ablation deposition, which I think is probably the best way to deposit bismuth, you end up being able to get high energy particles that don't have a huge amount of excess charge, so you can very effectively control them. But that's the way that they found it. That's the way that commercial thin films of bismuth are made right now. But my main point isn't putting them on substrates like sapphire or quartz. It's on creating materials or stacked layers of metals and oxides, where bismuth is one of those layers. And I need that in order to transport the wave. I need to transport the scalar potential across the material in a very, very fast way, so that we end up getting a force through, in this case, it's going to be magnesium and magnesium oxide layer in that order, and then the bismuth layer, so that we can get that field that propagates through the oxide layer as a boundary and then forces the electrons out down one side of the magnesium, where they will then collect towards the other side of the bismuth, and then they'll distribute themselves. So the stacked layer geometry will allow us to generate a sinusoidal input, but it'll end up creating a asymmetric force output because of the asymmetric acceleration of the dope junctions.
Well, hopefully we'll have our vapor deposition chamber up and running soon.
So are you talking about, you're making like something like a stacked capacitor where you have an insulator and an insulated layer and then a conductor layer?
It sounds like he wants to make the Linda Moulton House sample.
That's correct, Mark. Something very similar. Molten House sample, something very similar to it. Not quite exactly the same. I don't have the ability to drive a sample like that. I do have the ability to drive one that has one less material. So right now, I want to test the basic structure with bismuth thin film layer or monocrystalline domain layer, and then magnesium and then magnesium oxide. So it needs to be particularly those three. Zinc would also be a good additive, because zinc is also going to offer the same types of high drift velocities in a single domain lattice, just like bismuth will, but it's going to have a totally different electron density. So that could be a good transition material between the two layers of the boundary of the magnesium oxide and the magnesium. Oh, sorry, no, I got that wrong. Let me say that again. So in the boundary between the magnesium oxide and the bismuth, it could make a good transition layer, the zinc and the zinc oxide.
I'm sorry, I didn't hear what you guys said. What are you trying to replicate, Jeremiah?
There's a particular sample of materials which all demonstrate interesting dynamic nuclear orientation properties or high electron drift properties. Those two things together are definitely quite critical. So Linda Moulton Howe had been famous for having a sample that she was handed, which has been posted by many others, but she's the most famous one for talking about it. I guess she's, she who speaks the loudest or whatever, but point being, it's not really about her. It's about this sample that's been, pieces of it have been found, and she has one, and there's others that exist. And it's a stacked layer of zinc, magnesium, and bismuth. And also these layers contain oxides of all of those materials in a particular order, where the oxides are always predominantly on the top side, if you will, of the material of the predominant metal between them and the next layer of the solid metal, which then has an oxide on its top side, then another layer of different metal. So they're stacked in that kind of way, where they have these oxide layers, the main metals, and then that order of materials.
Interesting.
And it's not really that different if you think about it from the way that we make semiconductors today. Instead of oxide layers and semiconductors, which used to be the main way that we would make them, now we're using different types of dopants, and we can get rid of some of the oxide layers because it turns out they're not really the best. And that's how we got the GaN MOSFETs, some of the newest tech that really has super high efficiencies encroaching 99%, where you're talking junction resistances that are 0.0003 ohms at like 60 volts and have transition times less than 4 nanoseconds. So these are incredible devices, and we need bigger ones yet, but they're new yet, so we're waiting. Those will be the future, though. I mean, GaN FET technology, if it could be upscaled significantly, could be that technology that makes building spacecraft with human tech quite plausible, and would allow modular propulsion panels.
Gallium.
It looks like we're almost there with this part for the gyroscope. I just needed to thin out the outer diameter a little bit, 1/10 of a millimeter, and should be done now.
Oh, I'm in love with that CNC machine.
How could you be in love with it? You never even saw it.
I saw it long before it was ever at your shop, man.
You saw a picture of it.
I already know that machine. I know about
That
that.
little device to me.
You know, this is the first CNC machine I've ever seen or ever touched.
And it's a damn nice one. I mean, look, dude, just come on, look at that panel. Just look to your right. Look at that panel. That is a Starship panel. Look at that damn. If that's not beautiful, if that does not get the tech nerd in you all riled up, then you just ain't cut out for this tech stuff, man.
Why don't you come down to Jersey and you can play around with it?
No, I don't want to play around with it, but I do want it to make stuff for me. I want people that aren't going to break bits to play around with the code, and I'll sit there and watch it in mesmerization and thoroughly enjoy the process of that. Well, I watched something that was.
I smashed a ton of bits today. I think even the professionals do that, and I'm no professional.
Yeah, well, that's okay. Don't let me dabble in.
Damn, it's so
with
loose.
Works, and that means we need the bits that are going to be available while I'm there. So let me not break the bits, and instead, let's just make it happen.
It is way too loose now. Shit.
What's loose?
I made it too small. 1/10 of a millimeter was too much.
I will be helping you with the whole Perez antenna thing when I do end up coming down, though, because he's going to test that. It's not going to be his magic solution, regardless of how excited he is. He's going to need that fine structure. It's very critical to generate the types of localized stress energy he needs. I don't even know if he knows that, but I know that he needs it.
Well, he just went in for surgery and got like both his eyes, retinas or whatever shit replaced. So he's not doing any of that stuff anytime soon. Right now he powered it up and something was wrong with his amplifier and he didn't have time to fix it before going.
About that, I know I'm going to sound evil for saying this. I'm kind of glad.
What?
Well, because it gives us a chance to catch up and actually build it first, so that by the time he does have it working, we're not behind, because we'll have a replication of it. It's still his tech, but I want to be on that same page of having that drive too, because I have my own drive and I'm pretty happy with how it's going so far. But also I haven't replicated Perez's drive, and I would like to be able to validate any of that technology, because ultimately, if this stuff does come out in public, think about it. We've started the warp drive industry, right? That should be an industry that exists.
Yeah. I was telling Tom about it earlier, about the Cochrane, and he loved the concept of like having a 500 megacock spaceship, or we got really big, we'll get into the terracocks.
Yeah, well, that's not going to be up to you and me, Mark, to determine that. But
it kind of would be. It would be up to us collectively to get enough momentum going. David Perez loved the idea too.
Yes and no, but I'm going to take care of it on this end through the calibration community that I'm already well associated with, because we are literally responsible for making those units, and so we're connected to NIST, and we're going to tie it back to a standard, and we can do that. So I'm going to be working with that community when we have a drive that demonstrates a phenomena that does not have a unit value. And then I will demonstrate that to the technical advisory group that I've worked with in the past. And we're the ones that make the recommendations to NIST on how things should be modified. So we'll generate an officially recognized unit that will be NIST traceable for that, because if it's going to be an industry, it will need that.
And I think it's going to have quite a few parameters to it.
Oh, it will. But I'm in a unique position to do that, though.
It's not going to be like an amp, which is simply, volt time resistance or something like that. It's going to be.
Yeah, this is a 3-unit derivative. The Cochrane is a 3-unit derivative. It's a dimensional derivative that has to do with Cartesian coordinate space. It's a velocity derivative that has to do with propagation through Cartesian coordinate space. And then it's a temporal derivative that has to do with the amount of space that's inside that, or the displacement of that coordinate space over another volume. So it's how much matter can you displace in 1 unit volume of a chosen amount by exactly 1 unit volume at the speed of light. So if you were to take a cube, 1 foot by 1 foot, or 1 foot cube of matter, or a cube of empty space, it wouldn't matter, because the way the Cochrane is currently defined in Star Trek lore is that if you move that 1 foot by 1 foot by 1 foot cube of whatever is inside of it exactly 1 foot to the right, left, up, down, forward,
It wouldn't matter. You get it?
At the speed of light, if you were to move it at the speed of light, that is the equivalent of 1 Cochrane.
But it wouldn't matter.
What do you mean it wouldn't matter?
It wouldn't be matter, right?
Well, the idea is that the matter inside isn't affected, right? So, and the way we're going to do it is we're actually going to use the matter to generate that kind of force. So in our case, it's going to work a little differently. Like we could do it with something like the cells, where we have a device that specifically is modified, and the rest of the matter is encompassed in the field of this device, which is modified, so it's not the matter around the ship. Then you look at conventional crafts that we've been seeing for millennia, and they appear to be using the hull of their craft, which means that they're going to also be enveloped somewhat in that field. So I also have to ask, inside classic Star Trek lore, you have the time flow inside the craft flow at the same time flow as the outside of the craft, just like the Alcubierre motivation of the warp drive, which is what he based it on, was that lore. But in our case, I actually don't want that. I want to be able to slow down and speed up the time inside the craft. So. Oh yeah. But anyways, we'll have a definitive unit for the Cochrane. I'm going to go through the calibration community. We'll go back to NISC traceability and determine exactly what that is. And I know it's not going to be the same, because we do need to consider the molar energy of the energy density for any matter transferred at velocity c over 1 unit volume. And that's what we need to consider, is that the energy density is actually going to go up. So 1 Cochrane of lead is going to be, it's going to be like a millimeter. Well, 1 Cochrane of, say, feathers is going to be like, 3 meters.
It would depend on the material as well.
That's what I'm saying. I think that the actual unit will have to be derived based on the density of the material that's used, which would actually give us a realistically engineerable energy density number that does make.
I thought it just had to do with the space and the warping that you create.
And that's the whole thing with the drive, is I've looked at the time in the space-time surrounding it, and I'm not really sure if we could move some amount of matter within a volume of space without having to provide the equivalent energy of accelerating the matter through the, I guess you would call it, the boundary, through the horizon. Like getting the matter through the horizon takes energy. And if you look at it like Back to the Future way, you have to accelerate already to some arbitrary velocity compared to the stationary frame of reference, because you set up the field appears in the stationary frame of reference tied to everything else. So say in Back to the Future, the time warp tunnel, the opening of the gateway, appears in geosync to the Earth and geosync to the ground, but the car already moving passes through it, and its forward momentum carries it through during the gate time, which is only very short, enough to get the whole vehicle through, and then some airspace.
I'm not so sure about that. One way to look at it is you're not going to get free energy out of this device, but if you were to turn it on, let's say, and lift up 100 tons into 1,000 miles up or something like that, and it took a lot less energy than the amount of inertial energy that you got just from lifting it up, that energy is actually being pulled out of Earth's orbit, because you're now changing Earth's orbit. You get what I'm saying? So it's not free energy, but you're changing Earth's orbit now.
Well, okay, so I know what you're
free energy in terms that it's not costing you anything. But
I know what you're saying with that, but it's not necessary to do that. You could do this in deep space, at exactly the horizon between, say, two gravitational masses where neither one is really affected in either direction, and everything is balanced out. Anyways, yeah, I mean, eventually, yes, all of space will come to balance and the forces will come in and it's going to move the planet a little bit. But if you're doing it far away from all the matter, you can technically still do this phenomena. You can push fields forward and react against those fields because they do have a finite propagation velocity relative to you. So it is possible to generate energy out of the nothing, if you will. You can, in fact, pull power out of that by using the differential time field.
Without any effects on masses around you?
As long as you're outside of the information horizon, then that's correct. Yes, in the information horizon, things are affected, and that's specifically what you're using to generate your differential power.
It'll be a great way to solve the climate crisis. You just pull Earth into a slightly farther orbit.
The climate crisis is rectified with this technology because we will not be burning fossil fuels.
Did you hear South Australia was the first grid ever to go positive, meaning more energy was being created from all the solar and wind systems than consumed by the grid. It went like 35 megawatt positive.
Yeah, it was a tremendous debacle, and people are still on that one about how it's a bane or a scorn against green energy. And so my whole thing about this is we already have a power distribution system set up for every first world country. And it's not practical for everybody to just have a localized power distribution system. We're not going to go back to the days of Edison where there's a power station every 1 mile, because that wouldn't be any different than having a power station every 200 miles. But well, I don't think that it's also practical for people to have power control systems in their homes, because devices do eventually break down and there's going to be unforeseen problems, and it would be just an unbelievable debacle of a new industry, right? So instead of that, what needs to happen is the technology becomes realized, the primary contributors being vehicles need to change. So who's going to get hurt the most? Okay, so the gasoline industry is going to get hurt the most, and they're going to have to transition into something else a little different. They're going to have to start producing materials instead of burnable fuels.
Oh, talking about that, I just placed a reservation for the Ford F-150 electric.
Oh, amazing.
Really nice truck. Yeah, it has I think 150 or 200 kilowatt hour battery, and you can pull energy out of the truck. It has like 110 outlets. It also has a 240 outlet as well.
That's cool. But let me finish up with this one. So what would change in terms of the industries of this disruptive technology, if it were to come out, is that energy companies that currently burn fuels to produce power for the distribution grids would end up adapting these systems to produce that same power. They would probably start out by first having a technology that connects directly to the generator section, getting rid of the steam turbine, and then generating. And then the oil industries would transition from generating burnable fuel shipped over as, well, actually their crude would still come over to the States and stuff and other countries, but instead of burnable fuel, it would become plastics and more advanced material.
Bring it in. First, I want to have some dinner. First, I want to have some...
Hey, Wayne, what's going on?
I don't know if I got the pudding in the face.
Oh, I just muted him.
Thank you.
Yay, power of the
Host. Yes, that's indeed the good job of the host. Very much good. Very much good. Good indeed. I was surprised when I hooked up my handheld radio just to the antenna that I was getting almost the same kinds of volts per meter that I was getting out of the amp, yet the amplitude of the actual waveform I measured was nowhere near high enough. I really need to it's interesting. I really need to understand and separate out in my mind the magnetic components of the system from the electric components, because there is a significant difference. And they have a very huge effect on the transmission power. Even though technically my triple axis RF high frequency meter picks up the same volts per meter, when I'm transmitting with a handheld radio and that number is the same on that thing, I feel nothing unusual, whatever. But with the amplifier hooked up, because there's significantly more voltage there, even though my magnetic field intensity is the same, I really feel it. And it's obvious in my right eye, on the right side of my neck, and the right side of my body. And it's quite uncomfortable and lasts for many, many hours afterwards. And even though my meters would never detect it, there's another field that's taking place there, and it is not the electromagnetic photon field or the far field radio emission. There's something else going on there. I'm not even sure how I'm going to pick it up.
So what about Faraday cage, man?
Oh, Faraday cage is going to block me from it, but it won't allow me to necessarily measure this kind of unusual field. The equipment I'm using right now to measure the fields from both systems is showing that I have about the same output. So basically the meters are telling me that both systems are the same, but my observation on the oscilloscope and my observation in terms of its effects on my health demonstrate that something more is going on that's outside the conventional antenna physics that I've been able to find and study. Notice I didn't say that it's not out there. I don't know if it's out there. I would love to talk to somebody that's more of an expert on this than I am, that has some more advanced antenna physics background.
Sounds like David Fisher might be the person to go to.
Who's David Fisher about this guy?
Well, somebody mentioned him in the chat that he was actually here. He's one of my dad's old friends from Lakewood who worked on the fiber optic stuff for Bell Labs, and he knows everything there is to know about RF and fiber optics.
I would gladly take the opportunity to chat with him about this specifically strange issue. I think before I talk to
apparently he found out about APEC.
I'm so glad Bob, man. I spent so much effort trying to get Bob on, and the part that I'm sad about is that I have to go back and watch whatever he presented. And what really kills me even more is that I spent all that time trying to get Alexander on, and then I missed that one too. So it's like two people that I've worked on for almost, I want to say,
where were you?
For 8 months, sleeping. I was sleeping. I was up last night working on all of these projects, trying to get ready for APEC and possibly have a presentation, because I just got that material in, and I was so excited when I put it on the meter because it actually did the thing that nothing else did. It showed that decay, that leakage decay, and it was a time variant decay. So it starts out with a slightly higher resistance. Normally this thing drops straight from like, so the scale reading here on this device goes from 0 ohms up to 1 tera ohm. And
one second, check this out. Pinky bed. Pinky bed. Here, look at the Faraday cage. And I have actually 2 cameras in there.
Is this oh, look at the video of the Faraday cage. I need to look at my computer. Okay. Yeah, do that camera switch again. Let me see that. I wasn't looking. There we go. Hey, that's slick. Oh, dog in Faraday cage. Well, she's the safest thing in the lab right now.
I've actually been sitting here watching the doggy cam while you guys are talking for like the last 10 minutes.
Oh, what a joker.
Yeah, it was I managed to get the Faraday cage going. There was a problem with one of the computers. They just kept on freezing, so I took a different one. And then I had nothing to put in the Faraday cage. So I was like, let's put the dog in. So everyone has something to stare at. Pinky, bed. She's going to go back into her bed.
Yeah, I'm going to build
a doggy.
You remember that quote, Jeremiah? It says disclosure 22, and we didn't want to put 2020 because we weren't sure if it was going to happen. Honestly, I'm not even sure if it happened, because like there were some experiments that are kind of iffy.
Mm-hmm.
We might have we might have broken it in 2020, but it's more of a slanting slope, you know, kind of gradual shit.
Well, it's the thing. That's the funny kind of irony is like it's going back through history and trying to figure out exactly when it officially happened because it's already officially happened. I seen it when I was 12.
What have you seen when you were 12?
That's not disclosure, right? Because disclosure means.
What did you see when you were 12?
Oh God, where do I start with this? So let's start with the big ones. I seen two wires pass through each other, two solid wires with insulation.
Oh, I thought you meant you saw like a flying saucer or something. Yeah, you told me about that.
I'm not a witness. I've never seen an aerial craft that I can possibly identify as not an airplane or other aeronautic craft.
Tell us about the wires passing through each other.
What's that?
Tell us about the wires passing through each other.
Okay. So elevators require a lot of power for their DC motors. I don't know if y'all are familiar with elevator controllers, but they now use solid state. No, I shouldn't say DC motors, DC motor controllers, sorry. They now use solid state drive technology. So obviously induction motors, they don't operate at low RPMs when you put in a full frequency signal into them. So Allen Bradley and a variety of other companies make these solid state controllers that use huge DC filtering capacitors. AC comes in from the 3-phase line, it gets rectified. Our elevator here is actually 2-phase and goes into huge DC capacitor banks, and then those get power switched, square wave switched through PWM controller to generate variable frequency drive for the motors so that they can operate efficiently and lift people up. Anyways, I got a whole bunch of elevator capacitors, very large Maxwell 450 volt, 2,500 microfarad caps. And they're low ESR because they're designed for these pulse motor controller drives. And then at the lowest ESR, but they're pretty decent and have large enough terminals to be useful. And so I got those, and then years later, I got some more compact ones with even lower ESR, which means more turns with shorter leads and thicker terminals. And I put them all inside of a big ass box that says impulse generator on the side, painted it military gray with big old bold kind of cutout letters. And it's got a 30-foot det cord on it, little blue LED in there. So when you press the button, two brass electrodes 3/4 inches wide with huge lug nuts on them, take all the current from the capacitor bank at 1600 volts, 9,000 joules max energy. Technically, well, 9,000 joules, you got to hit 1800 volts, so slightly overcharge. But you hit 1800 volts at 9,000 joules. You hit the det cord, a huge contactor with one pad made of aluminum, the other pad made of stainless steel, hit each other. The reason why they're differential metals is so that they don't fuse, and the plasma EVOs that form between them push them apart, and they can kind of separate. There is actually a braking electrode too, a vibration electrode to break them apart if they do happen to fuse, because sometimes they will do that. But either way, so yeah, all the power from the capacitor bank is dumped into the electrodes, and anything that's between them basically gets all that 9,000 joules. Now, when I dead short them through a single piece of wire and I measure that current, I did try a shunt directly in there as an impulse thing. I ended up measuring 1.5 mega amperes, and the rise time over that was 4 nanoseconds. And then the decay time was the ringing oscillation that went down to about -1 mega ampere, and then up to about 0.5 mega amperes, and then down to about 0.2 mega amperes. So it swung positive more than it swung negative, but it ended up being about, like I said, about 1.5 mega amps peak on the positive side. And quite a bit of power. And in that system was able to do strange things, like allow wires to pass through each other and cause wires to become jellified. I guess it was just the sheer amount of current or momentum passing through or by that system, but it would apparently rip the electrons out of the wire and leave them in a depleted state. And in that state, they weren't necessarily hot, but they were soft. And one of those wires actually sneaked around the 2x4 as if it was a liquidy noodle. It made its way past the 2x4, took a 90 degrees turn, as in it bent at 90 degrees, almost very sharply. 12 gauge solid wire bent, and snuck around the corner, did another 90 degrees bend. The actual angle of the arc was only about 4 millimeters. And then it did a third one of those and was sticking out of the doorway. And so when I opened the door to see this wire sticking there and realizing it's solid, I of course held the wire in place as I opened the door to see what kind of damage it left on the wood. And it turns out it didn't really press into the wood. And I thought, how can a solid 12 gauge wire sneak its way, taking 3 different bends through the space between 2 pieces of wood and not damage the wood? Simple. It wasn't hard. It wasn't as rigid as copper. That's the only realistic explanation. It had forward momentum and the friction was low bonding. It's easy to see that low covalent bonds, less electrons, would still keep the material together, but not enough for it to be rigid.
That's pretty wild. Did you ever try to replicate that?
It's replicatable. Yeah. I have the impulse generator in storage. Mark and I even talked about, I'm working on a process of getting equipped here. And anyways, I have plans to actually drive that thing out. It's a 170 pound machine, and I'm not really sure if I even need to bring it out there to the Falcon Space Lab, or we can do more experiments there, because Mark has his own caps, and I think that it's an easy enough time for what he has out there in New Jersey, because I don't know how much you guys know about New Jersey, but it has a long standing history of this kind of research. So anyways, in Jersey, all we have to do is look hard enough and let people know that we're looking, and we can find our hands on very powerful pulse capacitors that vastly supersede the crap that I built. And we could easily put together a system that could replicate that much more consistently every time.
What were you measuring mega amps with?
I was measuring mega amps with a massive 40-pound shunt.
Yeah,
How old were you when you did this?
Oh, that's a good question. I think it was about, this must have been right around 7 years ago.
So yeah, for my job is I design motor drives. I'm not sure if I get you.
Michael, what's your job again?
I design motor drives.
Badass.
cool.
Which
For a second, I thought you said you designed warp drives. I'm like, oh, that's exciting. Tell me more.
That's my next job.
Well, you want to come work here at Falcon Space? We got some openings. Where are you based out of?
Pittsburgh. I work at the R&D department at Siemens.
Hey, a question for you. Like, you work in the R&D department. Do you guys, do you have ever access to, SCRs or large, not SCRs, I don't want SCRs, sorry, but yeah, those would be useful too. SCRs and IGBTs. Do you have anything that ends up getting like tested, maybe tossed? That's, I don't know if you have extra stock, overflow stock, but I know Siemens developed some pretty great drives. Siemens and Allen Bradley are both really powerful competitors in the industry with fantastic motor controllers. Do you have access to that kind of stuff? Because everything inside of industrial motor control technology is relevant to what we're doing.
Yeah, so we designed the best drives. But I don't know if I could. I never tried. A lot of my work is on a computer running simulations and things of that nature. But I can find out. I'll let you know.
Wait, so you run simulations on? Please tell me more about the simulations that you run. What kind of parameters do you look for? What can you test magnetically, electrically, systematically? Tell me what you are doing there, because I really want to know more about this.
Most of the stuff I work with deals with long cable applications. So what's that?
Transmission line stuff, inductance, reducing noise.
From the variable frequency drive to the motor. So if a company needs to run it down into the ocean bottom or something like that, it has to be a long cable from the drive.
Transatlantic lines.
Pardon me?
The transatlantic lines.
No, well, you mean that sounds like communication lines.
An underwater application. They're trying to do underwater welding cable or something, and they need to get power down there. Like they're they have some, they have some kind of submerged thing that's doing maintenance for like an oil platform or something, and it's got onboard motors or onboard controllers or something like that, or maybe it's a modulator or a valve they need to send power down to. The problem is that with these high frequency sharp waveforms, that long cables will attenuate that signal and cause harmonics and other problems. And it's not, what he's describing is that it's his job to figure out how to fix this issue that's a common problem in long transmission of high frequency motor control signals, which contain a lot of current, making it difficult.
Yeah, that's correct. So I will simulate them and I will determine what the signal will look like, and then how I can fix that with different size reactors and things like that, like inductors.
Oh, that's awesome. That's awesome. I would really like to talk to you more about simulation stuff. It sounds like you wouldn't really need to go far outside of your way or step on any company boundaries or put yourself in threat to do maybe some sidebar lunchtime or after hour simulation using the software that they have, which is like probably a $30,000 or $50,000 software.
Well, what I use mostly is ANSYS.
Don't know it. Can you describe?
Pardon me?
I'm not familiar with it. Can you describe it?
Well, it does a bunch of things. You can do, you can do circuits design. You can even design transformers in them. It's a large software. I can send you a link to to describe it better than I could probably in words right now.
I would like that. In fact, would you do me a huge favor? I know this is an ask, but would you please send me an email to exoticpropulsion@gmail.com with the subject line being motor drive simulation. I'll know exactly who you are, remember you, and then we can get in communication. I'd really like to talk to you more about this stuff. I have some stuff to tell you too that I think will really be interesting to you as well, so that there can be an even exchange and both of us are pretty satisfied with the education and the knowledge.
Definitely.
But I'd really
let me pull up my email and you can tell me the address. Or you know what? Can you put it in the chat maybe then?
Yeah, I will put it in the chat. And also, as I put this email in the chat, anybody else that wants to email me, also please feel free. I'm definitely down for learning and collaborating with people that are, especially in power electronics, who want to do this kind of technology, people who are builders and who have ideas that they've not been able to flesh out. Anybody that wants to email me, yeah, please feel free.
Here, check out these parts that I made today.
I'll check it out in a second, Mark. Let me finish typing this.
Oh, the last one is coming out right now.
Let me pull up Zoom on my computer. Okay, I can see you now.
Oh, 1 second. Yeah, so this is for the
yeah, please do email me. Dropped it in the chat.
Yeah, I'll email you right now.
Thank you. I appreciate it, Michael. Can't wait to talk to you. That's beautiful, Mark.
Yeah, these are for the Gamble device. Basically, it allows you to put the gyroscope at any setting over here, and this is the swinging arm.
Oh, so you'll actually be able to, those are heavy, by the way. You'll be able to control how far out the precessional axis is.
Yeah, or the torque axes.
It just wouldn't be funny enough if I didn't tell you. I told you so. Yeah, he was saying the same thing though. They've got to be off on this little offset, unfortunately.
I was basing it off of the diagram that he showed.
Yeah, it was deceptive. Well, what he showed you, Mark, the diagram was not for linear propulsion devices. He showed the diagram for satellite devices, and what you have is a satellite is a satellite orientation gyroscope. You can put that thing straight in a satellite right now, and you can reorient the angle and the axes of that satellite, but you can't make it move in one direction or the other.
Oh, check this out. I found that there's a company about 15, 20-minute drive from here that's making mini rockets for testing things in zero gravity. So they basically do the Blue Origin ride up into straight up into space and then back down again. So you get like 3 minutes of 0 G, but it's only for like CubeSats. And it's basically just a whole bunch of college kids that are building rockets in a shop right here in New Jersey, 15-minute drive from here, literally. So
Is it? So is
Yeah.
that whole arm swing back and forth, Mark? Show me how that moves in your hands. Show me where the mount point is and where the gyros are in your hands. Like hold it up for the cam.
one second, I'm just standing at mine right now.
Oh, okay.
I'm just sanding it down. Just give me a second. Finish that.
Because it's really big, thick, and heavy, and that's gonna really work against you.
Not very heavy, no. I could stick a couple holes in it. So basically, the gyro is going to be between two of these, and this is where the servo is going to be, and they're going to swing back and forth. And I'm able to put the gyros at any position. You see, there's multiple drill holes over here, and they're all going to be threaded. Over here was a bit that broke, but I'm not going to be using that hole anyways. So I'm just going to swing back and forth. And I made 4 of these, so I'll be able to position the gyros at any one position we want. So the gyro's over here, and it's going to screw into this and swing back and forth.
Okay, I'm just looking at that. Yeah, that angle was weird. I'm still having. Okay, that's the correct angle. So you're holding it up like that, and now hold the gyro up in the same angle, so it's like upright and gravity-wise where it's going to sit. Is just you kind of hold it at a serious.
Well, I'm going to remove this little chuck over here and put it in like that. So this is the pivot point against the base, and this is where the gyro will be out at the end.
And where is the adjustment then? How do you adjust it? If the gyro is at the end, or what are the holes for?
Oh, the holes are so that you can move the gyro in and out.
Right. So how? Show me, because you just put it on the end. So how can you move the gyro in and out if it's on the end?
Oh, well, there's the holes are set up in a way that you can. Well, you see, there's.
Show me that.
You see the 4 bolt pattern. So that pattern is repeated all the way down. So
you can think anywhere along the bar there.
Yeah, I mean, it's anywhere every 15 millimeters, I think, or 10 millimeters. Yeah, it can move into all these positions. But you'd have to switch it manually, removing all 8 bolts on each side, 32 nut bolts you'd have to remove in order to move the gyros to different positions. And I got 4 of them.
Wow, those are, man, that CNC does such a nice job, and you did a great job on the code. I'm very impressed with this. I really, every time I look at the outputs of that CNC and your work and the team's work on it, I am really genuinely impressed with it. And I like to be impressed. It's like one of the only things that makes me happy in life. So it's really nice to see, man. Good job.
Thank you. Thank you. Yeah, we'll plan on machining out the base for the vapor deposition machine on the CNC machine as well. That's going to be a 2-step process. We're gonna have to do it in like half at a time and spin it around. You can actually fit up to 23 inches of material on the machine, even if it can only machine 16.
Just a second. Okay, yeah. Yeah, so, just got, oh man. I'm almost just pulled in too many directions. It's kind of funny. Like I had this tape sitting behind me and I'm just staring at it, thinking to myself, when I tested it on the Megger and it actually worked at 2.5 kV leakage, and then it took almost 4 seconds to break down at 5 kV. It shows that property of that partial breakdown pulse. I'm thinking I'm going to tie it straight to a timer circuit, put a high voltage MOSFET on there, and then see what I can expect. Those little transformers.
You have too many projects going on simultaneously, don't we all?
it's going on, but in the case of the projects that I do have going on, at least they're ones that are tied to replications of papers that are well renowned and talked about in the community. In my case, all too often, I really want to get down to the bottom of these things that apparently work. People claim they work, but yet you don't see any replications anywhere from anyone.
It's always, yes, we had it, it worked, and then it broke, or then it was taken away or something like that.
Yeah, or like it's 3 years later and they're like, oh, we did that when we were in this lab. And now finally years later, somebody's paying attention when we don't have it anymore. And that's just not at all. Like, this is why I build power supplies into machines. This is why I'm not using bench setups with 1,000 banana jacks and all kinds of auxiliary equipment. Why I actually build a power supply into a machine, why everything is integrated and it runs off a battery, is the device simply, you hook up a battery and it's there. So years from now, when I want to pick that thing up, if it works, everything's there. I don't have to find all the equipment that I used to have. I don't have to, borrow it from somebody else. I just have to simply turn it on and it works. It's that famous phrase I tell people that I really ultimately want, the defining factor: push button, receive force. It should be that simple.
Amen.
So many complexities. Everybody's lost in the rigmarole of impossible chases. Too much adamantium or unobtainium, really. We got to get practical about this stuff, man.
Yeah, right now your minivans, you're out of titanium.
Practically, but it's not. It's also a low priority in the greater scope of what's going on.
I thought that's what you needed to get before you can come down to the Jersey lab.
Well, I've learned better since then. That still needs to happen before I can come down to the Jersey lab, but it's not even the biggest priority right
Also,
now.
there's a lot more stuff ahead of that.
Oh, it's not ahead of that. It's actually trumping it. It's that it almost kind of doesn't matter, because if one of these drives works, does it even matter? And when I'm looking at results that are already in the positive regime, and now, can you believe it? Wayne's got positive results too, and at least DNO. We don't know if it's an asymmetric force or if it's a reactionless force, but he does have an actual force. And he's got that force demonstrated in a way that completely rules out anything else other than magnetic orientation. So, like, that's a huge thing. Right now, Wayne is on the ball. I knew he was the right guy for the job, man. I watched Wayne for years, was subscribed to his channel before I even knew who he was, and I knew he was the right guy. But man, Wayne's got it, and he's got probably one of the most, what's the best way I can say this, objective viewpoints on this. It's truly objective in that sense, in a way that I envy and wish I was. Way that you and I, Mark, aren't quite there, but. Like, we have positive results. I have positive
I don't know how he finds the time to do it.
results. I don't either. The guy's got some kind of magic spell. I have no idea with the whole family how he finds time to do it, or how he has the concentration, let alone anything else, even if it's not time. How does he concentrate on it? I don't know, but I respect it. Best I can say. Either way, like I said, we have positive results now. What we need to do is get these things to the push button and ready, so that we can pull them out of a suitcase or out of a box, and they just simply turn on and work. That's what's going to make them ready for microsats. That's what's going to launch an industry around this stuff. Start small, but make something that works with a push of a button or a digital input signal, something that anybody can put on board their satellite and make sure that it never drops out of orbit. Or if it does, it drops out of orbit at a real fast speed and controlled directory.
I'm threading all my holes now.
But yeah. Falcon Lab in New Jersey is a stepping stone, but it's not that I need to get out there to do anything that I can't do here. I'm actually learning more here. And if I were to have come out there with what I've already done now, just in the meantime, where I didn't, I realized that I would have been totally befuddled and probably frustrated by what I was working on, because of the lack of stuff that I had here that I wouldn't have brought with me, having not realized that I needed it. And then
Like
I would have
what?
all kinds of orders and stuff.
Like what?
Like the super high frequency probe that I had to construct with the materials I had here, the electronics I had here, or with the special fiberglass tape materials. Or
What frequency probe are you talking about?
I built a special high frequency probe that can pick up the B flux of this antenna at 430 megahertz.
We have a probe over here that can pick up like 1 gigahertz.
Yeah, it's a oscilloscope probe, but you don't have the head for it. It doesn't have.
Yes, I do.
That's not. I'm not talking about a freaking clip lead, Mark. I'm talking about a specialty coil that picks it up.
Well,
I do need to get wire though. I do need, like, you have wire that I desperately need, especially that thick stuff that I need to build several Helmholtz coils for various tests. And if I like to 3D print those and build some Helmholtz coils, you should have some too. They're actually really useful, and you'll find that in our community, people will respect the use of Helmholtz coils for this field symmetry, and also because they allow you to view what's inside without really obstructing it. Best way you can avoid having to use a solenoid and still get a symmetrical magnetic field.
I also have people that can build you the Helmholtz coil too.
Oh, I know you do, and that's exactly what I intend to build out there. The Helmholtz coil. I want to build the Quincy photon spacecraft stuff. I want to get that 3D printed hull set up for that with the annular ring, and then I'll have to find a way to plate it. You got to get the cases printed for all the high voltage power supplies from the 3D printer. So, like, really, a lot of the work I want to do is on the 3D printer. It's plastic stuff, and that's just it's a whole thing about the geometry of getting the right parts in place. It's not necessary to machine them out of metal. It really just is going to be easier to make them as light as possible out of plastic.
Now we got lots of different types of plastic too.
Oh yeah, you have some great selections. I'm really excited about that. I'm excited about working with a 3D printer and somebody who knows how to program the code for it in the slicer.
Yeah, Tom McNevin knows how to do that too. Pretty good at it.
I figure somebody's always going to be around that knows how to do it, and even if there's not, you know how to do it. So.
Yep. That I do.
Yeah, my main goal of going out there is materials. It's just to make these things, and obviously that we can work on Elzaphan, but I think Elzaphan's still got a way to go. And I mean, just hell, look at what Wayne did. He didn't have any of that fancy stuff. He used a big old solenoid electromagnet, pretty large electromagnet, but still no core material, no iron, right? And he just had various samples in there, and he put a hand wound, like 6-turn coil in there to pump RF with from a signal generator. It only goes up to 60 megahertz. I'm ordering the same one so I can replicate his experiment almost exactly to just verify it. But look, he's getting repulsion forces from it. So if you look at Elzaphan's whole premise, the entire idea behind the paper that you're working with and the idea that you're trying to replicate, right? Elzaphan got what appeared to be a weight loss, but of course he wasn't measuring the weight of the entire EPR machine or the several ton magnets. He was measuring just the weight of the sample. And what Wayne just got was a force that proved he could push against the sample with the EPR magnet. And what does that mean in terms of Elzaphan? Well, if Elzaphan got an 80% change in the mass measured on the scale, where it lost 80% of its apparent weight, and Wayne just showed that sideways you could push on this sample, how do we know that? Simply in Elzaphan's case, he hadn't hit the same resonance and pushed on the sample, and by pure magnetic induction, just like, you know, a maglev train, he had levitated it that way or pushed up on it that way. And that's what we need to rule out. That's why what Wayne has done is really fundamental, and that's what we need to rule out with Elzaphan, which is a much higher frequency, but it could still be the same effect. And we want to make sure that that's not what we're seeing, because that's still Newtonian, you know. It's just like a maglev train. It's still a Newtonian device. There's
Oh shit. Looks like the holes that I made here are too large for the screws. Okay, time to go up to the next size screw then. Shit. It looks like the screws I got, yeah, the holes I made are too big. Damn. Gotta go to M4 now, or 3.5. Yeah, it's exciting stuff for sure. I can't wait to get something going with Elzaphan. The vacuum pump, that really nice one that I got, it's not turning on. We opened it up and found that there was a little water in it. So
oh no! Wait! Water where? Where was the water?
Was inside the vacuum pump. So we opened it up, got all the water out. The motor is like stuck. And I can't get it to turn at all. So we just
Dismount that motor. Yeah, you're gonna have to get inside there and get to the it looks like a little engine inside there. You're gonna see this arm, this pumping arm that moves back and forth for the diaphragms, and it's gonna have an eccentric on it. There's a slide in there, and it's really critical that whatever you do, you don't try to like just get it to the point where it's freed up enough to spin, because that slide bushing is probably a rust inside of it, and it'll just grind grooves inside of it. So first, clean it out with contact cleaner once you get it apart, and get all the rust out, all the crap out. You could even pour acetone in there if you wanted to, and just swish it around, empty it out. Spray it out with contact cleaner though, because that'll take out all the oils. Brake parts cleaner too, by the way. Brake parts cleaner also works very, very well. You have plenty of that. But yeah, make sure all the rust is out of the bushings.
okay.
I'm really sad that thing doesn't work right off the bat, especially considering what it is. I was thinking you could just simply plug it in.
Yep, I thought so as well, but apparently not.
Hey, good night. See you in 2 weeks, man. Sorry that I was 6 hours late to this one, and I got to go back and watch the whole thing later. I cannot miss all the stuff that was presented. And man, that really sucks that I missed Alexander's presentation. Was it any good?
I was listening, from the side. It was like, I had a whole bunch of other stuff going on, but he was having trouble with English, and he was talking about a ton of shit. Like, it sounded like he was all over the place.
I was hoping to be there to help correct that. I kind of figured it was going to be like that. And I have so many of Alexander's replications sitting here on the bench. I kind of wanted to collab and show what some of those things look like, because he's got these drawings, but he doesn't necessarily show. I'm guessing he showed his drawings and showed his paper, but he didn't actually show the devices, except for JLN's replications.
I don't know. I wasn't watching that intently to even
Yeah,
answer
it
that.
was a lot of diagrams on slides with a lot of text, and
Yeah,
he
so
talked about it, but he didn't actually show any devices at all.
I kind of figured, yeah, see, the thing is I have the physical devices that represent his diagrams, and I wanted to show those in conjunction with what he had. I tested them, by the way, and probably not surprisingly, they did not do what he claimed they did. I understand why they didn't do what he claimed they did, because there's Todd and David Chester, and we have better models that show what needs to happen. But either way, like, I wanted to actually show the physical representations to tie everything together, and I missed that. Maybe that's for the best. Maybe it would have been more of a clusterfuck even than it was if with the broken English there was somebody else trying to get in and show stuff, and Tim would have probably been overwhelmed. So I guess we'll save it. I'll watch it. I'll have good rebuttals. I'll try to get him back on there in a way that he can respond to what I'm showing. But I do want to address the Alexander stuff, because he's been around in this community for a super long time. Jean Louis Nodine had replicated his work, and so had other people, and they reported positive results. I reported negative results, and I feel like freaking Tamar or Hathaway Labs always reporting negative results, because I do these things with the education of Caltech and find out that when you eliminate errors, you don't get results. So that's why I'm excited about this shit that actually does work right now, that I finally have, man, because it actually does pass the Caltech test. It does pass the scrutiny.
It's pretty cool. He went over 18 different things. It was a lot of different stuff.
He probably touched Grebennikov for his hat design, his T-shaped capacitor, TT Brown, the oil and air differential device. Yeah, I'll watch it.
Yeah, you should do a follow-up presentation maybe, and go over some of the devices that you actually have. That would be pretty cool.
Oh, absolutely. Like my first intro, I think maybe one of the ones that got him on there was the gradient field drives presentation, which features specifically his stuff as well from 3 different labs. And 2 of the 3 labs reported some results, and I was the only one that reported null. So yeah, I will do a follow-up for it. I gotta watch it. Bob Greenyer. It's so freaking sad, man, after all that effort trying to get Bob on there, that I missed him. I know I said it already, but
yeah, Frolov showed up without his hat though.
That's okay. We've all Frolov's hat.
Bob didn't take any questions or anything though, so at least not.
I mean, he talks so much though that he had no time for questions.
Yeah,
And then in the open session, he just continued.
Yeah, he did. It was actually so. I mean, if you go back and watch the 2-hour presentation that he gave, it'll be the same thing. And then maybe we can get him to come back because he didn't even go over everything that he had. He was skipping things, and he went through it. He said this was as fast as he could go through it. So it'd be really cool to get him to do some more in-depth discussion about specific topics.
He seemed to be having a lot of fun too.
Yeah,
Yeah.
I thought he seemed like he enjoyed himself.
I actually try to see if I can get him to talk more about the tunneling effects, the transportation or teleportation.
Wondering about that.
I know that this community wants me to talk about teleportation more, and I personally want that. So I'll talk to him about that and see if he can develop more on a specific presentation regarding it. And then I also want to talk about the large or the macro scale transmutation effects that don't occur in vacuum. I replicated his ultrasonic device. So I built that thing. I have some videos of what it was doing, and it eats apart aluminum and other things that you stick in it. It's really interesting to watch. You get these aggressive little like rotating toroids that kind of run over the surface, and they'll literally take chunks out of the aluminum and slowly dissolve them into a fine powder. No, I don't have an electron scanning microscope or the ability to do metallurgical analysis on what ends up coming out of this powder that's produced, but I can tell you that some of it's magnetic. So it starts out as aluminum. That's obviously not magnetic. And then these super, super fine particles, they appear to be magnetic. And when Bob did scans of the same materials using standard kitchen foil and the exact same stuff that the rest of us replicators use, they found iron, they found silicon, they found tantalum, niobium, carbon, sulfur, and a variety of other things, and even smaller trace amounts like zinc and copper from what basically started out as a tungsten electrode. And they've also done the same thing with aluminum, had all these transmuted elements from aluminum, also the same ones. And it seems to be like they go through stages, they transmute from one to the next to the next. And
yeah, that is super interesting. In one of his videos, he went through and described the exactly what the ratios those things were appearing in, and it's the exact same ratios that they appear in the Earth's crust. Like there was a 1-to-1 relationship from what they were pulling out of the reactor to the likelihood of finding this stuff in like mines and whatnot.
that's fascinating. But now let's tie Bob Greenyer back to the Odic Ray, John Hutchinson, and ancient alchemy, and talk about transmutation of metals, which is something that is particularly fascinating because, in my opinion, if you look at, and if you want Star Trek technology for our real human future, we need replicators. And what do replicators do? Well, they convert matter into energy, and they take that energy and they beam it in a specific sense to create coherent fields that then become matter. And so really thing, right? But you have to have the control over those functions to convert one into the other and back again. And so if we look at EVOs as a transmutation device, being able to take apart and put back together matter, and we'll realize that the only thing holding matter together really is the electrical charges. You remove the electron cloud, the protons and the neutrons are now subject to impact and dissection, so you can take those apart and turn them into different elements. You put them together into the right geometric field by repelling them against magnetic fluxes and inject your electrons. Now they form molecules and now produce a new material. So in that sense, like, we have a real future in studying this stuff with replicators, real replicators.
Yeah, that's definitely the right track.
We think so. First things first, right? Let's prove it. Let's it's already proven that you can transmute elements. Let's prove that we can do it in a controlled manner. I hate to mention it because it's conspiratorial, but you ever heard of the Play-Arans? And this goes back to, I have to also mention another scorned name in the community.
Billy Meyer?
Yep, Billy Meyer, he's got it. Billy Meyer had a book he called Light Water, where apparently the book was inspired by the conversations he had with the Play-Aran Semyasi and a few others, but primarily Semyasi, feeding information to him and her constituents. And in things in a book from what apparently Billy Meyer claimed to be a farmer, a humble man. He took the bus. He was not exactly the kind of character that you'd expect to produce highly complex technical information. And so in the book Light Water, you scroll through it and get down to the meat and potatoes beyond all of the speculative stuff about relationships and intercosmological organizations and stuff. And you get down to the technology, right? And so he talks about specifically a set of frequencies and a set of metals inside of an oven. And what they're talking about is that within the normal stress energy tensor of the local gravitational constant that determines, local K of the permeability of space-time and the local temperature, that if you get a metal, say it be aluminum or silver or tungsten or gold or whatever metal you happen to start working with, you hold it at a certain physical temperature in relation to the outside reference frame. And as long as the physical temperature of the metal inside that reference frame is the same as the outside temperature is differential in reference frame. So they're basically not in a time gradient field. They're, in this case, simplified, that this is a normal field that you would just kind of have if you were sitting outside of your test equipment. This is like we're surrounded by this normally symmetrical field. So all good. It's an oven, effectively. You put your metal inside of an oven, you put a magnetic field across it to polarize the magnetic moments of the free electrons. And that's all it does, is polarize magnetic moments of the free electrons. It doesn't really do much for the rest of the valence shells. And then you inject it with a microwave signal from the side at a temperature. And what will happen is the material will harmonically start to ring like a tuning fork, which you can pick up with a pickup coil to know when you've hit it. And it'll start to transmute into other elements as electrons are lost. And in order to neutralize out the extremely strong mechanical vibrations, protons and neutrons break off into other elements that then are pulled away because of their charge differential by the external electrodes and collected. So apparently you can transmute elements this way, and it's all in that book Light Water, which is totally out of place for that book and totally out of place for a farmer. Meyer to be posting. And it's not just him that posted the same kind of tech, which is why I'm saying it corroborates. It's not Billy Meyer's tech. He's one of the people also who has talked about taking a metal, heating it up to a specific temperature, heating it with a RF field under the influence of a magnetic stationary field, and then causing it to transmute over the course of several minutes to several days, being held at that temperature as a result. And this is how we take Bob Greenyer, which has all kinds of EVO transmutation happening across the board, many different elements, because each EVO event is a destructive event where it decays over time. So you end up doing a transition across many elements, and whichever one it ends up with, where it doesn't have enough energy to go to the next, that's what it stays on. And you take that and refine it down to controlling the exact temperature. Why does Bob Greenyer's EVOs transmute metals into different metals instead of always the same one? Because the temperature of the EVO and the amount of electrons in the cluster is different. It starts out with more energy and more heat, and it decays down into less energy and less heat. And as it does so, you get lighter and lighter elements towards the state where it piddles out, but not with the temperature system. If you hold the element at the right temperature and keep the same element transmuting, and you don't get this piddled out effect. That's the trick.
Okay.
Are you saying to take off to open up the motor itself over here? Or should I just remove the motor from the compressor part?
You need to take it all apart, Mark, if there was water in it.
I'd remove it from the compressor and then take it apart if you can.
It's very difficult to open these screws over here.
It's difficult, and you got to do it. I took apart my vacuum pump when I first got it too, and had to do the same thing. Just get intimate with your pump, man. Take every single thing off. It's a one-day project, and it's a particularly useful pump that's very rare and extremely expensive. It is worth your time to do it.
Just can't get these because these screws
Don't
have like.
screws. You should be using an impact drill, dude, with a right socket.
Yeah, there's no socket for this. It's like a flathead. It's like a flathead screwdriver there. Oh, you know what I could put? I could just use a flathead screw on a drill. How about that? Let me see if I can find a large flathead screw.
Oh, cool. Okay, I just got a link that I have to click on real quick.
Oh. Is it gonna give you free car insurance?
No, but it will offer me a chance to talk with somebody I highly respect.
Extended warranty. We've been calling to talk to you about your extended warranty.
Okay, I need to open edit. And I need to go to this link.
It's probably the saddest job in the world. To be scamming people over their car's extended warranty.
No, there are worse folks out there than insurance scams.
I believe it's a form of like pinging you to a GPS coordinates to verify that you're there. So they send a signal, your phone rings, you pick it up. Now they triangulate where your exact location is. You know, that's what I think it really is.
Lulu, you know what I'm doing right now?
What?
I'm going through this super organized machine hardware box, looking for some parts.
I didn't know what they were labeled, but they're all like separated very well.
They are separated very well, and now I can find one. Here, this one looks useful.
And by the way, I got you how many boxes like you're gonna need, and you know how it's gonna look like. But I couldn't find a place where they actually sold those dimensions. But I found a place that can manufacture them. But I didn't want to give them that because we could do that like in the lab. Like we could create a number for it.
It's a lot of work. Yeah.
Like, you know, so I don't want to, I mean, I don't know. I could like call like somebody that can, you know, make the exact.
Yeah,
dimension.
get us some quotes, because like it's a lot of work to make all those shelves.
There is like in Houston, just like simple search, like a place where they manufacture these, like the plastic, you know, the different, all sorts of different kinds of plastics, and you know, you choose whatever you want, and they'll make it out of that, you know, with the exact dimensions you need and all of it. So cool. I mean, I already like got the numbers mathematics wise. Oof. Yeah, you're gonna need like two different sets. You're gonna need like one set of 10 by 12 by 6.33, but the 0.33, it just depends on, you know, how you break it down, you know, whatever metric measurement you're using. And then you're gonna need about 54 10 by 12 by 6 inches. And they stack into exactly the space that you have. I mean, they'll just fit in at like 9 by sets of threes in threes.
Oh.
Yeah. So yeah.
Smith.
Here, look. This is some pictures. Like.
Oh wow, you actually took
Yeah.
measurements from it.
Where,
Oh my
Yeah.
god.
Oh, here, let me pin her.
What Jeremiah, what
Real
she's
quick.
talking about is putting shelves over here to slide in and out for all these boxes, make it easy, more accessible.
Yeah, and like, you know. Yeah.
Lulu, can you forward those dimensions to companies that are local to here and see, you know, get like quotes on how much it would cost?
Yeah. Okay.
That's a great way to.
Yeah,
great way to get this
but
done.
they'll look really, I think they'll look really, really good. You know, you put them on rails, like you could pull the things like 2 sets of rails. You want the top rails, so you it puts less weight on the bottom ones. So you have one from the top, one from the bottom, and they just slide out. And you know, like you know, just makes it easier like that. So you have two different ways you could do that.
Yep. Yeah, makes sense.
Yeah. Oh, that's what I was gonna mail you these. I had an envelope ready. But yeah, I'll let you know.
Super.
What are you working on right now? The gyroscope?
No, not the gyroscope. I'm working on the what do you call this thing? The I'm trying to open up the
Vacuum pump.
vacuum pump. Yeah, vacuum pump that broke. And in order to do that, I need to make myself a tool. Pinky bed. Pinky, go back to your bed.
I have one of those, Defiant.
What, you have a dog?
Yeah.
Pinky bed.
Like she's outside. She won't come in. She's stubborn as like dogs can be.
Okay. I'm gonna put down my headset for a second.
I have a 130-pound Rottweiler, and he's really nice, and he's usually pretty well behaved. But he kind of only listens when it's like convenient for him.
No, she thinks playtime is all the time.
Oh yeah.
Oh, yeah.
Why is this not working?
Okay, so going back to the transmutation of metals. So the design that I'm most familiar with for LENR is the ECAT design in like a ceramic tube. And so it's kept under pressure and it's exposed to a magnetic field at 60 hertz and tuned to a square wave, or at least in some experiments, that's how it was done, with nickel, and it resulted in the creation of isotopes of nickel. In other designs for other reactors, they did come up with other elements like you suggested, but I don't know how those work. So it might have been more similar to what you were talking about. So it's really interesting. So I wonder if it wasn't kept under pressure in the oven, it was exposed to microwave radiation instead of an electromagnetic field. Do you know what the frequency was, or the like the waveform or anything like that?
Yeah. Oh, as far as the transmutation of the elements at temperature?
Yeah.
Yeah, the frequencies are listed in there and the temperatures are too.
Okay, cool.
If you want me to, I'll just pull it up real quick and I'll just read, because you're just kind of curious as to the generalized idea of how achievable it is. And let me just pull up light water and I'll just type in a search for the term megahertz. Let's see, that'll stuff about 1.45.
No, it's not working.
They were meant at least 30 or 40 discrete frequencies at random and consistent frequency shifts that range from 4 to 2,170 hertz. Let's see, that's varied. That's those ones. Okay, this is for propulsion and the interferometry patterns they were getting in the time matrix. Let's go on. Okay.
This is a book, right?
Here we go. Okay, yeah, the transmutation, the lists. Okay, so here's just one list they give. And they're talking about, okay, so we start out with an element. In this case, the source isotope is silver. It turns into the target isotope gold. The resonant frequency at which silver turns into gold is 38.93181 hertz, or 38 megahertz. 931, 841 hertz. So it happens at 108 degrees Fahrenheit or 43 degrees Celsius. If we wanted to, however, turn zinc into gold, we have to increase that temperature of the zinc to 673 degrees Fahrenheit or 356 degrees Celsius and hold it there very precisely. And we have to hit it with exactly 39 megahertz, 126 kilohertz, 761 hertz.
So what's so special about gold?
I was just giving gold as a reference. If we wanted to transmute zinc into aluminum, we would have to take the zinc to 362 degrees Fahrenheit as compared to gold, which is 673 degrees Fahrenheit. And then we would hit it at 39.293 2963 megahertz instead of 39.1267 megahertz. And so in one case we get gold at a higher temperature, in the other case at a lower temperature and a slightly higher frequency we would get silver, or excuse me, aluminum. Yeah, this whole chart is a cross reference. There's a bunch of different cross here. But the funny thing is, you look at this book, it's so obscure, right? And the reason for why this fairly scientific paper looking chart is in here makes no sense. But then there's right above it a picture of somebody who apparently tried it in an oven and using a microwave transmitter. They've got pictures of the two side by side against a ceramic bowl, and one looks like silver and one looks like gold. So I don't know. To me, we have microwave equipment and these frequencies are not high. I mean, they're 40 megahertz. They're practically CB radio frequencies, you know, and then all you need is cold temperatures. So how hard is it to hit a metal with a CB radio frequency slightly above there, you know, long wavelength ham radio stuff, and then hold it at a certain temperature? Like,
how do I get a copy of this book?
Light water, I can send it to you. It's not huge. You seen that post that I put in there, exoticpropulsion@gmail.com. You send me a copy, send me an email to that email I posted in the public chat, and in the subject line, light water book. And then I'll remember to send you the light water book. I'll copyrighted so you can't share it, but I'll be glad to send you with this. The reference is on page 106. I'll include the number in the email.
Okay.
Yeah, the most thing I seen was the whole bismuth to gold thing. That definitely got me interested. Aluminum to gold is interesting enough, but bismuth to gold is really, that caught me. It always seems easier to take protons and neutrons out than it does to, you know, combine them together. That seems like a lot more complicated process to take something that's lighter and turn it into something heavier than it does to break something down.
Yeah.
Bernie claims that he got stuff that aren't on the the table of elements.
They don't show up on the table of elements if you do a standard electron microscopy on them. If you use a synchrotron to try to measure them, you'll get wrong readings. That's because in the monoatomic state, we derive a lot of the informational data about frequency response for precession or photonic reflection from particle sizes based on their bipolar chemistry. So like say gold, for example, does not, you don't find gold in single atoms, generally speaking, just like you don't find oxygen or nitrogen in single atoms. You got the N2, O2, CO2, C2, you know, things like to bond in pairs at the minimum or more. And when you have individual atoms, the way that photons interact with them is quite different. So they don't show up on the types of equipment that we have to measure bulk metals and bulk material, bulk elements. But they're just as much those elements as their multi-atom constituents. It's just that the equipment we design to measure them doesn't work right for those types of materials. But they're not impossible materials. They're just, you know, monatomic gold is just much gold as biatomic gold. Frisco gold.
Don't tell that to Bernie though.
I told that to Bernie. You know, I told a lot of that stuff to Bernie. Bernie somehow I guess Bernie got funded to some reasonable extent from somebody, which was great because I hope that he shows up and does something with it. But he got funded enough where the point is, I think that Bernie could be able to produce some outcome with that, and I'm hoping that he does. Because I'll tell you who sent me some stuff, man. Our community alchemist, who the guy who I actually consider the professional in this. We've got man, I only got like 2 hours of sleep last night, so
You know, they manufacture like pills of monatomic gold, like you could take for your health. They say like in ancient times that it brought cellular regeneration, like you could like stop time and not age. So, you know, that's how.
That was David Hudson's claim. David Hudson was the guy who developed the Ormos technologies. He used primarily Dead Sea salt to create M-state elements. That's what he kind of deemed them. But M-state elements, by his descriptions and seminars, are monoatomic elements. And David Hudson claimed that when he put these materials on a sample dish inside of a gas-controlled environment with non-oxidizing elements, and the sample was heated to different temperatures, that the weight of the sample would change, and at one point, while being electromagnetically perturbated with some high frequency input from the outside, where they're trying to measure exactly what was going on, you know, what elements were present, you know, just like any other NMR machine, it has a coil surrounding it, it's inducing the material to a magnetic field, and then they had the ability in this particular machine to change the temperature. So what they found is, induced at certain frequencies, the material would literally disappear and the weight would disappear as well. And then apparently if they cooled it back down and they shut off the RF field, after some time, the material would just reappear right on the sample platform and it would pick up the weight again. The thing is that leads to speculation about things that I don't particularly like. For example, if the material becomes weightless, but it's still on the sample platform and it's also photonically invisible, then you should be able to scoop it off. But he says, or he claims, that they passed something through it at that point, through the area where it should have been, and there was nothing there. So if it was invisible when it was there, then it would have been scooped off. But here's the problem. The sample platform moves up a little bit. When the material would disappear off it, say it disappeared, the sample platform is actually going to move up in physical space. And so if the sample were to reappear on it, it would have to reappear inside the sample platform, because now the platform is existing in a space where the sample previously was. So if it does reappear, how does it reappear on top? That part to me doesn't make much sense. Just like a teleporter, it's like, how do you know what the destination of your teleported object is exactly? And is it going to be half inside of a bulkhead or something? Like, you don't want to teleport your legs into the bottom of the bulkhead and just be sticking out of it, right? We have.
Isn't that what happened with the Philadelphia experiment? Yeah.
Right. So that's what we don't want to do. And that's it. When Hudson talks about this effect, that he tells that story, I bring into question whether or not there's possibilities of that, because it doesn't actually make sense how you could have a material reappear or rematerialize on a platform where the platform is physically moved its geostationary location from where it was. So there are issues I have with the reports, but the good thing is that our community alchemist, he has sent me 6 different material samples, and some of them include monoatomic gold and monoatomic copper. He has several different batches, and so it's a very small amount of each, but I do have the vials here, and in order to make sure I don't lose anything, because it's such a small amount, luckily the scale is sensitive enough, I need to be careful about how I set up the experiments. The good news is setting up the experiments for this particular test with these M-state elements is going to be the same setup I use to test the molybdenite. So a small audio amplifier that can only go to about 40 kilohertz using a linear chip, and a 2-axis electromagnetic coil.
Never check that out. Just made another tool bit.
Oh, let me go back and get that open, since I was just reading the charts there. Let me pin you so I can see this. Pin. There we go.
Okay. Whatever.
That out. Yeah, cool. Screw. Flathead screw that's been widened out with the Dremel. Very good.
Not with the Dremel. I was using there was actually a hex. I had to round it out as well. Needed
Good job.
enough metal over there in order to grab it.
No, that's a good solution.
It's this, there's one final screw left, and it's being kind of a pain in the ass.
Anyways, you've got an oven and you've got aluminum, so I figured, shit, we should try this transmutation thing. That little oven, I don't know if it's.
Oh, it
got
worked. Ah, yeah.
Yeah, buddy,
Thanks.
way to go.
First try. That worked. Yeah, I always tell Tom Butler here that whenever you have a project, more than half the job is finding the right tool.
Oh man, absolutely.
Sometimes you got-
Creativity is always a challenge too, especially when you're coming at the echelon of what's already been done by other humans. You have to always push the boundaries of what's possible because the answer is not out there. At least in an accessible way. I mean, obviously there's always an answer out there somewhere very deep within projects, but it's whether or not we can actually get to it. So we've got to get pretty creative in finding ways to do uncommon things with common materials. The funny thing is the Horizon drive is going to work with freaking tape. The material, by the way, the special material, I won't exactly mention what it is a type of tape. It's just a very very special type of tape. But
What's the Horizon drive again?
Mike McCullough. The Horizon drive is a solid state particle accelerator drive that uses as its particle accelerator leaky dielectric.
Okay.
No moving parts, takes in DC high voltage, produces a force as a result, and produces a gravitational field if not allowed to move. So it can produce artificial gravity theoretically on a spacecraft, and it can produce the force to move the spacecraft as an impulse engine.
Sounds exciting.
I'm excited. I got the first of two things in, and I can't tell you how happy I am to see this material sitting in front of me. I've been wanting to get my hands on this stuff for years. I just never knew where exactly to get it. And luckily somebody in our community contacted the authors of that paper and asked them what they used, and they instructed. I got that exact material, and here it is sitting in front of me, just literally showed up. So I was hoping to get it done by today so I could actually show it on the pendulum, but that's okay. I don't even feel the need to do that quite so fast. I'd rather do a better job because my leakage tests tell me already that it's doing exactly the thing it was reported to do. And of the 12 other materials I tested, none of them did it. So this particular one doing it, that tells me right off the bat that there was validity in this paper. And now I'm very excited to verify that it's true.
Exciting. Trying to open up this motor here. Oh, it's not easy to open it up.
Oh, Mark, I wanted to ask you a really important question too, after you get done with that motor, but I'll let you think about it while you're working on it. I need to pick up a quality and decently accurate, reliable magnetic field meter. It's just one of those tools that I should have in the lab, and I do not have one. I've looked online to see the many options, as you have spent many hours doing. And because you have more experience buying shit meters and good meters than anybody else in the magnetic field meter stuff, I need to know what your recommendations are. What one or would you recommend, if any, or are you dissatisfied with all?
I like the Alpha Labs one the most so far.
Is it highly reliable?
It's hard to say because the numbers do like jump around a lot, and it's hard to like until I get dynamic nuclear orientation going, that I can't say for sure that, hey, you know, that one was off by 10% or 2% or whatever, because And, I would base that off of the known gyromagnetic ratio and say that the field was actually a lot stronger or a lot weaker or whatever.
I suppose if I can manage to, maybe I'll just buy some, but maybe I'll get some of that thin film bismuth, or maybe I'll even find a bismuth Hall effect sensor that's remanufactured. What would be cool about that is that I could.
What would be cool about it?
All of a sudden he muted himself.
Oh, his phone does that sometimes. Jeremiah, you muted yourself.
So I did mute myself. You're correct. Yeah. Did that happen in the middle of me talking?
Yeah. All of a sudden you cut off in the middle of a word.
Wow. And you know what's really screwed up about that? In order to mute myself, I have to click on my screen, and I have to, when I do that, it pulls up the hidden menu at the bottom, the taskbar that has the mute button on it, and then I have to click on it, and that didn't even come up when it muted. So, well, can't trust the phone either. Oh well, can't trust it.
Bugs.
I guess when you get into this stuff and you start to have something that works, it's kind of inevitable that all your shit's going to get hacked up. That's why I'm seriously concerned about how I communicate with people, because, oh God, man, the data security seems to be impossible. It's like no matter how good you are at researching this data security stuff, no matter what you look into and how many billion and one ways you learn that you can get hacked, the truth is that the very best of the best people with almost unlimited budgets are going to be, of course, better than the best stuff that you can find online and the best things that you can educate yourself on. They're literally paid to be able to hack the hackers. That's the problem, man. It's almost unavoidable.
Hey guys, I'm just popping back in. You're still at it.
Hey,
Tim. Oh my God! It looks like I fixed it. Look at that.
Show me.
Well, I loosened something up and now it's spinning.
Nice.
Wow.
Hey, sure,
So
man.
let me ask, with this conference, when I cut the ending of this, should I just go all the way through here, or?
No, I want you to end the recording. We're going to talk about some stuff off air, if you would.
Yeah, let me do that. I'm going to stop the recording right now.
Yeah.
Okay.
We've said stuff I think can be public. We haven't said anything that was sensitive information, and it could even be useful to people. But going forward now, I think we want to transition into talking about
Yeah.
don't want out there.
Yeah. Well, another great conference in the can, guys.